This video is divided into 14 parts. Their times are listed in the video description and in the comment section below. Enjoy! Part 1. Acid Ionization and Strength. In this video, we will be dealing with the Bronsted-Lowry acids. So these acids donate an H+ to the solution. And the H+, this H+ right here, is usually referred to as a proton because the H atom from which it is derived loses its electron. So you can see the H atom lost this electron. This electron is separated from the single proton that the nucleus of the H atom consists of, and only the proton is left. So when H becomes H+ by losing an electron, there is only that proton nucleus left. So H+ are usually also called protons. The general notation for a Bronsted-Lowry acid is HA. When the Bronsted-Lowry acid reacts, it usually ionizes and dissociates. That means it separates into ions. And typically, in this case, it would separate into the H+ ion, because the Bronsted-Lowry acid yields an H+, and the A- ion. Since the A- is a negatively charged ion, we call it the anion from the acid. This is the basic reaction that the Bronsted-Lowry acid undergoes. However, when an acid dissolves in water, the reaction on top here is not representative of what actually happens to the acid, since in the water we have water molecules interacting with the acid. What actually happens is that when the acid dissociates into its ions, the H+ ions that came from it bind to the water molecules drawn here, and this binding action forms the hydronium ion. These H's right here bind to the H2O to give the H2O an extra H, and this forms the hydronium ion in water. Meanwhile, the anion from this acid remains floating by itself, well, at least in this case. So the acid strength depends on the concentration of the H3O+ ions in the solution. A higher concentration signifies that the acid had a greater degree of dissociation and a greater strength. In order to measure the strength of the acid dissociation in water, we have to use the equilibrium equation for the dissociation of the acid. And here is this equation. On the top, we have the products of the acid dissociation in water. So here are the products of this reaction, and they are on the top of this equation. And on the bottom, we have the reactants of the acid dissociation reaction. So here are these reactants, and we drew them at the bottom, and they're drawn as a product. And also, all of these have these brackets surrounding them. The brackets signify the concentration of the substances. So basically, the brackets mean that here, whatever number we write here, will signify the molar concentration of the substance. For example, if there was a number 1 written here, that would, or let's say right here, there was a number 1 written, then we would say that there was 1 molar of A- in this solution. This equation is used to show the concentration of the substances after the reaction is complete. And the reaction is complete when an equilibrium is established, meaning that the rates of the forward reaction and the rate of the reverse reaction are equal, and the concentrations of all of these substances remain constant at that equilibrium point. Only then can we use this equation. So this equation right here is this formula right here is equal to Kc, the equilibrium constant. And the equilibrium constant basically measures how much this reaction went, let's say, forward at equilibrium. Let's say it measures the ratio of the product of the concentrations of the products to the product of the concentrations of the reactants. So this ratio at equilibrium, and that is Kc, the equilibrium constant. As you can see, the more of these H3O plus hydronium ions produced, the greater the Kc, because a greater amount of product means that this fraction will become greater because the H3O plus increases in value here, and this Kc value will also go up. And well, let's say if that's the case, then if there is more of this H3O plus and then the Kc is higher, then this acid is stronger, because that means that it dissociated more to produce more of this H3O plus, raising the value of the Kc. So a higher Kc equilibrium constant means that the acid is stronger because it dissociates better. However, we do not use this equation to represent the strength for acids. This is because we can make an approximation. Since we are dissolving the acid in water, here's the acid, here's the batch of water we're dissolving it in. There is already a ton of water, there's a lot of water, and not so much acid. Therefore, although the concentration of the acid changes significantly in the reaction because there's so little of it, the concentration of the water changes very little, since an extremely tiny portion of it is used up in the reaction due to the tiny amount of acid relative to it. So let's say we dissolve a little bit of this acid, yeah? Since there is so little of the acid relative to all this water, even though we used up some of the water when this acid dissociated, this change in water is relatively tiny in comparison to the total amount of water here. Therefore, since the change in the concentration of the water is so ridiculously small relative to the total amount of the water already present, we can multiply this concentration of the water by the Kc right here. Why can we do this? Because this H2O right here doesn't really change, this concentration right here, because there's just so much water already present that it's a little bit of acid dissolved doesn't really change its concentration. It's negligible. So we assume that the H2O concentration here remains constant. So we can multiply this H2O concentration by the Kc at a certain temperature, because these Kc's vary with temperature. But let's say at a certain temperature. And from this we'll get another constant called Ka, the acid ionization constant, which shows the concentration of the ions produced from the acid dissociation relative to the concentration of the acid left. So since the concentration of the water here remains constant, we can multiply these two to also get another constant value. Since both of them are constant, we get a separate constant called the Ka, the acid dissociation constant. And this acid dissociation constant shows the concentrations of the H3O plus produced by the acid times the A minus concentration produced by the acid over the concentration of the acid that is left over after this reaction went through. So let's say some of this acid dissociated and produced H3O plus and A minus. we would have this portion on top and the HA on the bottom. And we would measure the relative amount of H3O plus times A minus over versus the HA on the bottom, which whatever concentration of that acid is left over. So this constant is easier to use when representing the equilibrium concentrations of the reactants and products of the acid dissociation reaction. In effect, when a lot of this acid dissolves, dissociates, the concentrations of the products on top are very high. Because if a lot of this stuff dissociates, then we get a lot of this and a lot of this. And when we got a lot of these products, this product of the products, this multiplication of the products, increases in value. And because of that, the Ka also increases in value. And basically, when the Ka increases in value, it signifies a stronger acid. Because it shows that this acid on the bottom, this acid right here, is better at producing these H3O plus and A minus ions, hence increasing this numerator on top and increasing the Ka value, which signifies a strong acid. So, and when a lot of this actually dissociates, very little of it, let's say, remains. So this denominator decreases and this numerator increases. So the Ka really increases for a strong acid because it dissociates so much. And let's say that if the acid dissociates very little, so most of this remains and very little of these are actually produced, then most of the acid remains. So this value on the bottom is higher, and these values on the top are lower, because there's so little of these products actually produced. And because of that, the Ka is also lower. And if the Ka is lower, it signifies a weaker acid. So in effect, what we get from this is that the larger the Ka, the stronger the acid. It's better at dissociating. The smaller the Ka, the weaker the acid. It's worse at dissociating. Let's move on to part 2, determining the ion concentrations and the pH of an acid ionization. Usually, the Ka equation is used to find the H3O plus concentration. And this H3O plus concentration can be used to find the pH of this acid solution. Well, now, why is that? It's because the concentration of H3O plus is equal to the concentration of H plus that came off the acid. And all of this H plus binds to water to form H3O plus. So essentially, the concentration of H3O plus is equal to the concentration of H plus. So we can use the concentration of H3O plus to find the pH of the solution. Now I'm going to show you how to solve for the H3O plus concentration when we're given a certain concentration of an acid. And so let's say basically we have 0.4 molar of acetic acid, HC2H3O2, in solution. So it's dissolved in our solution. The Ka for this acid, its acid dissociation constant, is 1.8 times 10 to the negative fifth. And we need to find the H3O plus concentration first, and then the pH. So to solve this problem, we have to know first what actually happens when acetic acid dissolves. So when this acid dissolves in water, it produces H3O plus, the hydronium ion, and its anion, C2H3O2 minus. And here's this equation for it dissociating. And we know that this extra H right here, this extra H, comes off this acid, and it goes to H2O to produce H3O plus, and leaving this part with only C2H3O2-. So that is how the reaction of the acid goes in water. Now remember, when we dissolve an acid, that does not mean that the acid dissociates. Dissolving and dissociating are two different things. So when we dissolve this, only a portion of it actually dissociates. We can dissolve the entire acid, but only a portion of it actually comes apart and forms H3O plus and C2H3O2-. That is called dissociating. So based on this reaction, we can draw the equilibrium equation for the acid, which we can then use to find the concentration of the H3O plus. Now we know that we draw the products multiplied, the concentrations of the products multiplied, H3O plus and C2H3O2-. And then we draw the concentration of the acid remaining on the bottom, HC2H3O2 on the bottom. This is the concentration of the acid remaining after the equilibrium has passed. So, however, we do not know how much of this actually dissociated. We only know, here it's given, the initial concentration, which is 0.4 molar. And we're also given the Ka value. So we can plug in the Ka value right here. Ka is 1.8 E minus 5. And we can plug in the 0.4 molar as the initial value of this acid, HC2H3O2. And we do not know what concentrations of these products are produced, so we just plug X and X for them. And I'll explain why it's the same X for both of them very soon. So because this 0.4 molar is only the initial concentration, but this concentration right here is at equilibrium once the reaction already proceeded, we have to draw 0.4 molar minus X, indicating that some of this initial concentration of this acid is lost because it dissociates. So it has to be 0.4 minus X. And obviously we replace the Ka here with 1.8 E times 10 to the negative fifth. So why do we draw X and X here? Why is it the same thing for both of these? Well, when an X concentration of this acid is lost in this reaction, it reacts. When an X amount of this acid reacts, an X amount of H3O plus and an X amount of C2H3O2- is produced. Because these are in a 1-to-1 ratio. Here, HC2H3O2 is in a 1-to-1 ratio of H3O plus, and it is in a 1-to-1 ratio of C2H3O2-. That means that for every X of this dissociated, an X amount of H3O plus gets produced and an X amount of C2H3O2- produced. Hence, when we took an X away from here, an X amount of this 0.4 molar initial concentration of acetic acid, an X amount of C2H3O2- is produced and an X amount of H3O plus is produced. An X and an X on this side. But we do not know these X's. We do not know how much actually gets produced. But we do know that the same amount of concentration that gets taken away here is produced on top of here. Hence, we draw an X and an X for both of these reactants, since they're in a 1-to-1 ratio with this acid. And now, we can just simply solve this equation to find the X, the concentration of both of these products. And once we find the concentration of both of these products after the reaction goes to equilibrium, well, then we know the concentration of H3O plus, and that is already part of the problem solved. And that is exactly what I'm going to do here. First, I take this lower portion and multiply it by 1.8 times 10 to the negative fifth, right here. Then, I distribute the 1.8 times 10 to the negative fifth within the parentheses. So here I distribute it and multiply by the 0.4 to get 7.2 times 10 to the negative sixth. And I multiply the 1.8 times 10 to the negative fifth by the minus x to get minus 1.8 times 10 to the negative fifth times x. So I distribute it to each one of these terms. And here I multiply these x's on top to get x squared right here. So this is x squared. And now I will actually bring this x squared to the same side where we got most of where we have most of these numbers. So it's going to be minus x squared because we brought it to the other side. So in effect, we get this equation. It's actually a quadratic equation. It's minus x squared minus 1.8 times 10 to the negative 5th x plus 7.2 times 10 to the negative 6th. And we know that anyone who took algebra here knows how to solve a quadratic equation. And in case you might have forgotten, I'm here to remind you how. Basically, we recognize that the coefficients here can be assigned like a letter. So a equals -1, this is the first coefficient. B equals the second coefficient, which is this one because it has this x to the first power. So it's b equals -1.8 times 10 to the negative 5th. And c is the last coefficient because it has no x's close to it. It is 7.2 times 10 to the negative 6th, and it's positive. And now based on this, we can plug these a, b, and c, the numbers that correspond to them, into our quadratic equation right here, which you might have probably learned in high school, although you might have forgotten by now. And we know that negative b can go right here, times negative here, and a and c, and a on the bottom. And we essentially, from this quadratic formula right here, this equation, we get one x and a second x. And we need to choose which x is correct. Well, actually, when I solved this problem, I got two of these x's. I got a positive one, 0.00267 molar, and I got a negative one, negative 0.00267 molar. Which one is correct? The correct one for any of these concentration problems is always the positive one. You never choose the negative one because it's impossible to have a negative concentration of a substance. The concentrations have to be positive. And also the concentration here produced, let's say both of these x's are positive, then you choose the x that is less than the initial concentration of this acid. Because since the acid dissociates in a 1-to-1 ratio to the product produced, you cannot have more of this concentration produced than the concentration of the acid initially. That would be physically and chemically impossible. So in this case, the concentration 0.00267 molar is significantly lower than 0.4 molar of the initial acetic acid concentration. Now, that would be our concentration of H3O+. However, if, let's say, you do not want to actually solve this quadratic equation on paper, since I will admit it does take quite a while, and you might not have that time on the exam, I will provide you with a shortcut to solving this quadratic equation. Since most of you are probably using calculators to solve these problems, there are some apps you can use on your calculator to solve these quadratic equations. First, I'll show you how to solve it on your scientific calculator and then on your graphing calculator. So, for our scientific calculator, let's say, I would turn it on and then I can go and press second right here, second, and then I will go to the blue right here that says poly solve. So you can see it says poly solve on top. It's the cos button. And here we have these quadratic equations we can solve. But we know that this quadratic equation right here is the x squared form. So we click on the first one. And we can just plug in all of these coefficients right here into here to get it automatically. So for the first one, we have -1, so -1 entered. Then we have the second one, B. It's -1.8 times 10 to the negative 5th, so -1.8 minus 5. And then for C, we get 7.2, -6. And these are all of our coefficients entered here. Now we can just press solve, and boom, we get the x's for this equation. The first x is 0.00267, just like here. And the second one is -0.00267, just like here. Now, on your graphing calculator, there is a similar thing. And it depends on which calculator you use, but I believe most of these graphing calculators have this function built in. If you do not have it, I think there's a way of downloading it online. So you have to go to the apps button right here. And once you go to the apps, you scroll up and you go up to number 9 right here. It says polysimult. It's polynomial simulation 2. And you click it, and then you click it again. And then you go to the first one option right here. You go to poly root finder. And you go to the second order. All of these problems are going to be second order because it's x squared. So you go second order. And you can click this button right here to go to the next. And then you put in all of your coefficients right here. So the first one is -1. The second one is negative 1.8 times 10 to the -5. And the third one is 7.2 times 10 to the -6th. And now you just click this again and press solve, and again you get the same thing, negative 0.00267 and positive 0.00267. They're basically the same, but you have to take the positive answer here. So that is how you do it the short way. If you're pressured for time on the exam, you don't have to solve all of this stuff. You can just show that you're going to solve it via a polynomial and just get these answers. Okay? Now that we know the concentration of H3O+, we can find the pH in this problem. In order to find the pH, we'll use the formula negative log of the H3O+ concentration. You can memorize this formula by knowing that the P in pH stands for negative log of something, and the H obviously stands for the H+ concentration. When you combine the P and the H, you get pH, and that will be the negative log of the H+ concentration. We also know that the H+ concentration from the acid equals the H3O+ concentration in this solution, because all of the H+'s combine with water to form H3O+. Therefore, the pH of the solution equals negative log of the concentration of H3O+. So, we just simply plug in this concentration of the H3O+ into the negative log formula, so negative log of 0.00267 right here, and we get a pH of 2.573. Now for significant figures of the pH, the rule goes that the number of significant figures in the concentration is the same number of decimal places in the pH. So here we have 1, 2, 3 significant figures in our concentration of H3O+. Therefore, we have 1, 2, 3 decimal places in the pH. So the number of significant figures in the concentration equals the number of decimal places in the pH. That is the significant figure rule for these types of problems. Now, believe it or not, there is an even easier way to solve this problem to find the concentration of H3O+. And this way involves an important approximation. And this is a very important method because it's very frequently used on exams where there's a time pressure and you have to solve things quickly. And sometimes you do not have the time to solve the quadratic equation, it's just too difficult. So this approximation will make this problem extremely easy to solve. So again, we have our reaction on the top where HC2H3O2 dissociates to form H3O+ and C2H3O2-. Previously, we determined that the concentration of this H3O+ for this problem is 0.00267 molar. Now, we can solve this problem a different way. But we start out with the same step initially. We draw our equilibrium equation here, with the Ka equaling the two x's on top for each one of these, x times x, and on the bottom the 0.4, the initial concentration of acetic acid, minus x, the concentration of it that dissociate to form the x on top and the other x on top. Now here we do not have to write 0.4 minus x, surprisingly. In fact, we can take away this x to just write 0.4. Now why is that possible? It's because that when we previously saw that the concentration of H3O plus formed is 0.00267 molar. And since X of this concentration formed 0.00267 molar, then X of the same X of this concentration was taken away. So this minus X is equal to the X on top. So if 0.00267 molar formed on top, 0.00267 molar was formed on the bottom. So if we were to plug in 0.00267 molar for this X on the bottom, we would get 0.4 minus 0.00267 molar. And this would give us 0.397 molar. Notice that the change here is very small. We only change from 0.4 molar to 0.397 molar. It's so close that 0.397 molar can actually be rounded to 0.4 molar. It's just essentially the same. It's essentially no change because this X is so small. It is so ridiculously small relative to this 0.4 because 0.00267 is much smaller than 0.4 molar because so little of this acid dissolved that the concentration of this acid, this 0.4 molar, changed very little, only to 0.397 molar when the equilibrium was established. However, when we need to find the X on the top, we can actually take out this X because there was so little of this X that it essentially does not affect the lower part of this equation. And therefore we can get rid of this X and just pretend as if the initial concentration of this acid stayed the same. Because it essentially did. It's just so little of it dissolved. As you can see, so little of it actually dissolved in this reaction that we can approximate here that the X was negligible. And we can take it out here and just keep the 0.4. Otherwise, for precision, we can just put 0.397, but that won't make much of a difference in what we find for X, because 0.397 and 0.4 are virtually the same. So we take out this X on the bottom, using our small number approximation, because we know that this X is so ridiculously small that we don't need it. And now this becomes a lot easier to solve. All we have to do is multiply this 0.4 by the Ka, so 1.8 times 10 to the negative fifth times 0.4. And this equals the X squared. The X is on top. And we get 7.2 times 10 to the negative sixth after that, because 1.8 times 10 to the negative fifth times 0.4 is 7.2 times 10 to the negative sixth equals X squared. Then we square root the 7.2 times 10 to the negative sixth to find the X. And the X would equal 0.00268 molar. It's slightly different from our previous answer of 0.00267 molar, because we took out this X on the bottom. But is it really that different? 0.00268 molar, it's basically the same as 0.00267 molar. It's so similar. So it becomes, and on the exams they usually accept both answers. So you can either solve it the quadratic way or this easy way where you don't need the X because it's just too darn small on the bottom. So you can just keep this 0.4, take out the X because it doesn't make a difference on the bottom. You can just find the X on the top. And that is why you don't have to solve the quadratic equation. And that is why this is the easy way. And you get the answer 0.00268 molar. And it's very fast actually. You can do this very fast. Just solve this equation that's much faster than solving a quadratic. But we cannot always use this approximation, unfortunately. We cannot always assume that this X is so small that we can ignore it. We can only use this when the initial concentration of this acid, this 0.4 molar right here, is equal to or greater than 100 times the Ka times this 1.8 times 10 to the negative fifth. So if this initial concentration of the acid is 100 times or more greater than the Ka, then we can use this concentration, because that means that this Ka is so tiny in comparison to the initial concentration that so little of this acid dissolves that we do not actually care about this minus X on the bottom. We can essentially keep the initial concentration of this acid. And in this case, the 0.4 molar is obviously much greater than 100 times 1.8 times 10 to the negative fifth. That means that so little acetic acid dissolves that we can essentially ignore this x and solve this problem. And this is what I call the small number approximation. It is very simple to solve and is much simpler than solving the quadratic equation. And I would recommend using this for any problem where you can use the small number approximation. Very simple to solve. Part 3. Common ion effect on acid ionization. Furthermore, another type of problem that might be asked is to find the concentration of anion that an acid produces when dissolved in a solution of a certain pH. This problem might be asked because not all acids are dissolved in solutions of pure water. Some are dissolved, as can be seen here, in solutions that already have an acid dissolved, another acid dissolved. So they're dissolved, this HA is dissolved in a solution that already has a high concentration of H+. So basically what this does is that, let's say an acid dissolves in regular water. This acid releases a bunch of its H+, they combine with H2O to form the hydronium right here. This reaction right here goes really forward, like it goes full speed ahead like normal. But let's say the acid, this acid right here, is dissolved in water with a lower pH and more H+ that are already dissolved. So all of these H+, yeah? And these H+ by themselves already combine with H2O to form all of these hydroniums, H3O+. So there's the problem. If this water is already like crowded up with these H+, the acid has a more difficult time releasing H+, because this water is already crowded with H+. It's kind of difficult to shove more H+ into the crowd. And basically this forces this reaction, to go more backwards, to shift more to the left. So this reaction shifts more to the left because these H+ can't get released that much from this acid in a solution that is already filled with these H+ already present. It's kind of difficult to release more H+ into a solution that already has a lot of H+ and a low pH. And that is what is known as the common ion effect. We know that the acid releases an H+, and this solution already has H+ prior to when the acid was added. It already had a lot of H+. Since H+ released and H+ already present are the same ions, these are common ions. And if there is already a common ion in the solution when that the acid releases, let's say this ion in solution is already the same as the ion that the acid releases, then when the acid actually dissociates in the solution, it already has a more difficult time giving away its ions, dissociating, because there are already a lot of the same ions already present in the solution that already crowd up the solution, not allowing so many of these new ions of the same type to get added. And that is the common ion effect, and it reduces the dissociation of this acid in solution. And now we're going to see how we can solve problems to find, let's say, how much acid dissolves in a solution that already has, let's say, a lot of these common ions, a lot of these H+ present prior to the acid dissociating. Now let's say we have the following problem. We have 1.5 molar of acetic acid, HC2H3O2, with a Ka, because acetic acid has a Ka of 1.8 times 10 to the negative fifth, and this acid is dissolved in a solution with a pH of 2. So this is an acidic solution. So we need to find the concentration of the C2H3O2- ion released by the acetic acid when it is dissolved. So in order to solve this problem, we first have to understand what is happening. In this case, the reaction for the dissociation of acetic acid is HC2H3O2 combining with H2O, and that will yield H3O plus and C2H3O2 minus, because the H from the acetic acid combines with the water and creates the H3O plus. And the equilibrium equation for this reaction is H3O plus times C2H3O2 minus on the top, and the final concentration of the acid HC2H3O2 on the bottom. This is at equilibrium. But in this case, since we're dissolving this acid in a solution with a pH of 2, that means it already has a lot of H plus ions in it, and therefore a lot of H3O plus. That means that this concentration of H3O plus, there's already a decent concentration of H3O plus in the solution. And that means that this reaction shifts to the left because there is already a crowd of these H3O pluses present, and it's difficult for this acid to dissociate more. Hence, if this acid dissociates in a solution with a pH of 2, which already has a lot of H3O plus, not so much of these are also going to get produced, the C2H3O2 minus, since there is already so much H3O plus that the acid's going to have a difficult time coming apart in the solution. So how do we find the concentration of the C2H3O2 minus ion released by this acid when it's dissolved in a solution of a pH of 2? Well, we used our Ka equilibrium equation again, like we did for our other acid problems. We know that the initial concentration of the C2H3O2 is 1.5 molar, as mentioned here. 1.5 molar acetic acid dissolves in the solution. And we know our Ka, which is 1.8 times 10 to the negative fifth, and it's mentioned right here. Furthermore, we know that if the solution has a pH of 2, that means there are already a lot of these H3O plus ions present initially. So we need to find that concentration of H3O plus measured initially to find out how much additional H3O plus this acid adds when it dissociates. And to find the concentration of H3O plus that are present at a pH of 2 initially, we know that the pH equals 2. We know that our pH equation, negative log of the concentration of H3O plus equals 2, the pH. So in order to solve this logarithm, we take 10 to the negative second power, because this logarithm has a base of 10. It's like a hidden little thing right here, but it's actually a base of 10. And we do 10 to the negative second power, and we get 0.01 molar of H3O plus initially present. So we write 0.01 molar of this H3O plus already present. And this is at the initial point, like there's none of this C2H3O2 minus yet present, because these are just the initial concentrations. We do not know how much of this will be present in the end, so we just write an X for it. So we obviously know that this Ka equation is not for the initial concentrations. It's not for when the acid was 1.5 molar, it's when it actually dissociates to make more of this and more of this. So to find these final concentrations, we just do what we did previously. 1.5 minus X, because a certain concentration of this acid dissolved, and it produced an X amount of this C2H3O2 minus. So we don't know how much, but we know that it produced the same amount as the concentration of the acid that dissociated, because it's in a 1-to-1 ratio. So minus X, and here it's plus X. And we know that in addition to that, it produced an equal concentration of this H3O plus. So if an X amount of here dissociated, an X amount here got produced. So an extra X to this 0.01 got produced on top. Because here H3O plus and C2H3O2 minus are in a 1-to-1 ratio, so these X's are in a 1-to-1 ratio. So an X of C2H3O2 minus gets produced, and an additional X of H3O plus gets produced, which gets added to the already present concentration of 0.01 molar H3O plus. However, if you are going to solve this equation, good luck to you, because that is, I mean, you can solve it, but it might take a while, and you might not have that time on the exam. So we will use our small number approximation. In this case, we know that the initial concentration of the acid is definitely more than 100 times greater than this Ka of 1.8 times 10 to the negative fifth. It's definitely more than 100 times greater. That means we can take this x on the bottom right here out. We can cross it out right here. Cross it out. Because this x is negligible, because the initial concentration of the acid is so much greater than 1.8 times 10 to the negative fifth that so little of this acid actually dissociates that this minus x, we don't need it. The bottom value essentially stays the same. And we can do actually the small number approximation on the top. Since this initial concentration of H3O+, the 0.01, is definitely more than 100 times greater than 1.8 times 10 to the negative fifth, we can also cross out this plus x, because the amount of H3O+ added here is very small. It's in fact negligible, because the Ka of the acid is so much smaller than the initial concentration of H3O+, that whatever x is added here essentially does not change this initial concentration. It's just so small. So we can also cross out that x. And in the end, we get 1.8 times 10 to the negative fifth equals 0.01 times x over the 1.5. So let's go on to the next step. Now that we know that 1.8 times 10 to the negative fifth equals 0.01 x over 1.5, we can multiply 1.5 by 1.8 times 10 to the negative fifth, and we will get 1.8 times 10 to the negative fifth times 1.5 equals the 0.01 x on top. And then 1.8 times 10 to the negative 5 times 1.5 is 2.7 times 10 to the negative 5, and this equals the 0.01 x. Divide the 2.7 times 10 to the negative 5 by 0.01, and we get 0.0027 molar of this x. And this x, remember, was the concentration of C2H3O2 minus that was produced by the acid. So our answer is 0.0027 molar of C2H3O2 minus that was produced by the acid when it was dissolved in a solution with a pH of 2. So that is how you solve a common ion problem for an acid. Part 4. The nature of polyprotic acids. Not all acids, like this acetic acid, dissociate by forming only a single H plus ion. Some can release several H plus ions, like this phosphoric acid that releases a whole 3 H plus ions, and these can have multiple dissociations. Acids that can release more than one H plus for each acid molecule are known as polyprotic acids. So, for example, in this case, H3PO4 can release 3 H pluses. When it is dissolved in water, the H3PO4 can give 3 H pluses to the 3 water molecules that are required for each H3PO4 molecule, and this yields 3 hydroniums, because 1, 2, 3, 3 hydroniums, and the PO4 3 minus anion. However, this reaction is deceptively simple. This does not actually happen when H3PO4 dissolves in water and then dissociates. What actually happens is that this reaction, this total reaction, happens in many steps, and this is important, and I'll explain why. Usually, when this phosphoric acid dissociates in water, it does so in multiple steps. It does so in this case in 3 steps. So in the first step, the H3PO4 gives an H to the H2O, forms an H3O+, and gets left with this H2PO4-, which lost an H to the H2O, which made H3O+. Then this H2PO4- can lose another H to the H2O to form another H3O+, and this H2PO4- now becomes HPO42-. And then this HPO42- can lose another H to the H2O and this forms another H3O plus, and this HPO4 2 minus transforms into PO4 3 minus with all of the hydrogens completely removed. Now, why does this acid not just release all of its H ions in one go, like in this reaction? Well, this is because right here, after H3PO4 lost one of its H's to H2O to form an H3O plus and H2PO4 minus, you can see that the H2PO4 minus has a negative charge. H3PO4 is neutral, but H2PO4 has a minus charge. Since these H's, these H ions, are positive, it becomes more difficult for this H2PO4 minus acid to lose additional H's because it is negative and the H plus is positive. So to take off another H, like in this reaction, it becomes more difficult because this negative charge pulls back these positive H pluses that get pulled off. So each time you tear off a H from the H3PO4, it becomes more and more difficult to remove an H plus because this thing becomes more and more negative from -1. So first it becomes -1, then -2, and it becomes more and more difficult to take an H away from the H3PO4, and then the H2PO4 minus, and then the HPO4 2 minus, because these get more negative and pull the H pluses back stronger. And that's why H comes off one at a time. Now, because it becomes more and more difficult to take an H plus away from these more and more negative acids, the Ka's for each of these reactions is different. In fact, for the first reaction, the Ka is the highest because it's the easiest to take off an H from H3PO4. Then the Ka for the second reaction is lower because this is more negative and it's more difficult to take away positive H pluses. So this Ka is lower. And then the Ka here is the lowest because this is the most negative portion right here. And therefore it is even more difficult to take off an H plus. And therefore this acid here dissociates very poorly because it does not really tend to yield H pluses because it's so negative it tends to pull them back. So the Ka3 here is very low. So these Ka's for each progressive reaction are labeled Ka1, Ka2, Ka3. The Ka1 is much higher than Ka2, and the Ka2 is much higher than Ka3. Essentially, the progression goes like this, where the Ka1 is higher than Ka2, and the Ka2 is higher than Ka3. And these are very large differences on many orders of magnitude, usually for these types of polyprotic acids. So now that you know how the strength of these reactions differ, you can see how, let's say the H3PO4 on its own is a weak acid. So most of this acid remains undissociated. We can also see that basically the H3PO4 concentration is going to be pretty high here. It's going to be one of the highest concentrations of substances in the solution. Furthermore, since the Ka1 for this H2PO4 is the highest out of these Kas, the H2PO4 minus concentration is also going to be fairly high than, let's say, HPO4 2 minus concentration, the PO4 3 minus concentration, since more of it gets produced because of a higher Ka. It is then, of course, used up, some of it's used up in the second reaction, but very little because the Ka2 is significantly smaller than the Ka1. Also, another ion that is pretty common here, relatively common than, let's say, the HPO4 2 minus and PO4 3 minus, is the H3O plus. Because again, each of these reactions contributes H3O plus to the solution. So you can say the most common ions in this reaction are the H2PO4 minus and the H3O plus ions. And A common substance would then be water, obviously, because this entire thing is happening in a large amount of water, and the H3PO4 that we added, since it's a fairly weak acid. Now this is what happens when this polyprotic acid dissolved in water. The H's come off one at a time, and there is very little, let's say, of this PO43 minus and very little of this HPO42 minus, because the Ka's are very small. However, if this polyprotic acid, H3PO4, is combined with a base, a very strong base, a strong base, like NaOH is sodium hydroxide. It's a very strong base, and it tends to really grab these H's away from the H3PO4. Then we essentially ignore these K1, K2, K3. Because let's say we add enough NaOH to take away 1 H from this H3PO4, it is gonna take that 1 H away no matter what. No matter what this Ka1 is, this NaOH, let's say 1 NaOH added to 1 H3PO4 molecule, is definitely gonna take that H away. So you see the H plus gives off, the OH minus of the NaOH takes this H plus and forms H2O. Now let's say we add H3PO4 to 3 NaOH. 3 of these for every single molecule of H3PO4. In this case, since there are 3 of these OH minuses, it's going to take all 3 of these PO4, no matter if the K2 is lower than K1 or K3 is lower than K2, no matter if it's harder to rip off, it gets progressively harder to rip off these H's. This NaOH, because it's such a strong base, it's going to take all of these 3 H pluses at one time, and it's going to produce 3 water molecules, because 3 OH minus and 3 H plus form 3 water molecules. So basically, to keep in mind, I just want to say, in the future you might have to use this, is that when dissolving in water, yes, the Ka1s do matter. But when dissolving this phosphoric acid in a strong base, the relative differences between these Kas don't really matter. All you have to know is that if there is only enough NaOH to get one of these H pluses from this H3PO4, then it will take this one H plus, because these H pluses do come off one at a time. But if there's enough NaOH to take all 3 of these H pluses, it's going to take all 3 of these H pluses. One at a time, yes, progressively, because again, these Kas do become weaker. And this acid does give off H pluses one at a time. But because there's such a strong base, it's going to rip them off. Like, there is no question about that. All of them. It's not like water where a lot of the stuff remains undissociated. The base is so strong that it rips off these H pluses fairly easily. So if there's enough base to rip off 1, it's going to rip off 1. If there's enough base to rip off 3, it's going to rip off 3. It's not like water where a lot of these H3PO4 remains undissociated and the H pluses are kept by this H3PO4. The base completely takes them away. Part 5. Determination of the concentrations of H3O plus and anions of a polyprotic acid. So let's say that we would like to determine the concentration of H3O plus ions that a polyprotic acid produces. So how would we be able to do that? Well, here I'll show you an example problem to show you how we can determine the concentration of H3O plus ions that a polyprotic acid produces when it is dissolved in water. Let's say we have 4 molar of H3PO4, otherwise known as phosphoric acid, that dissolves in water. The Ka1 for this acid is 7.2 times 10 to the negative third. The Ka2 is 6.3 times 10 to the negative eighth. And the Ka3 is 7.1 times 10 to the negative 13th. And we would like to calculate the concentration of H3O plus in this solution. Well, first, again, like with any of these problems, we have to understand what is happening when H3PO4 dissolves in water. Now we know from the previous part that there are three reactions that actually happen. Each time the H3PO4 loses an H, so to the water, and makes H3O plus, and then it makes H2PO4 minus, which then again loses an H, that makes another H3O plus, and that yields another HPO4 minus, since this H2PO4 minus lost an H to make HPO4 minus, and then the HPO4 minus loses another H to water to make another H3O plus, and finally we're left with the PO4 minus. And each of these reactions has a different Ka. There's a Ka1, Ka2, Ka3. And these Kas progressively decrease in their magnitude as we go from reaction 1 to reaction 2 to reaction 3. We also have to notice that the Ka1 is much, much greater than the Ka2 and the Ka3. In fact, as you can see here, the Ka1 is 5 orders of magnitude greater than the Ka2, and the Ka2 is another 5 orders of magnitude greater than the Ka3. So essentially the Ka1 is much greater than Ka2 and Ka3. You see, the 7.2 times 10 to the negative 3 is much greater than these two other values. So it's so much greater. And that basically means that this reaction happens to a much greater extent, to a much, much greater extent than these other two lower reactions. So although each of these reactions contribute H3O plus to the solution, we should probably only care about this first reaction, because it produces the most H3O plus. In fact, it produces so much H3O plus relative to these other two reactions that the H3O plus that is produced by these other two reactions is essentially negligible, because their Kas are so tiny relative to this first Ka1 that basically, even if we do find the H3O plus concentrations produced by these, they don't really matter. They're not really going to change the overall value of H3O plus produced, because this value of H3O plus produced is so much larger than these other H3O pluses. Their addition is not going to make much of a difference. So if we know that only this first reaction really matters, then this problem becomes a very simple problem, because we only need to find the H3O plus concentration produced for this reaction. And then it becomes like a simple acid dissociation problem. First, we'll have to draw the equilibrium equation for this first equation, and that will be Ka1 equals the products multiplied by each other, the concentrations of them, so H3O plus times H2PO4 minus, over the concentration of the reactants, so H3PO4, and we ignore the water, as always. Now we just plug in the values, so 7.2 times 10 to the negative third is the value of Ka1, and that will equal to the initial concentration of the H3PO4, which is 4 molar, minus X. And for every X of this acid that's dissociated, an X amount of H3O plus gets produced, and an X amount of H2PO4 minus gets produced. However, due to our small number assumption, the approximation, we know that the 7.2 times 10 to the negative third is actually the 4 molar initial concentration of the H3PO4 is more than 100 times greater than the 7.2 times 10 to the negative third Ka value for this. Therefore, we can ignore this minus X on the bottom and take it out, and our equation becomes 7.2 times 10 to the negative third equals X squared over 4. Now we just multiply this 4 by 7.2 times 10 to the negative third. We get 0.0288 equals the X squared. Take the square root of the 0.0288 and we get 0.1697, around that to 0.170 molar of H3O plus. So the concentration of H3O plus is essentially 0.170 molar for the 4 molar of this phosphoric acid that was dissolved in water. However, things become a little bit more tricky if, let's say, the exam asks us to find the concentration of one of these anions. So this H2PO4 minus or HPO42 minus or PO43 minus. And see, there are plenty of anions that the exam could ask about, and it can ask to find the concentration of HPO42 minus or PO43 minus, and we need to know how to find the concentrations of these anions. So in this case, let's say that the exam asks us to find the concentration of PO43 minus, and I'll give you an example problem showing how to find that concentration. So to illustrate how to find the concentration of PO43 minus, I'll use our previous problem with the phosphoric acid. In this problem, we have 4 molar of phosphoric acid, H3PO4, dissolved in water. Here are the different Kas to K1, K2, and K3 of phosphoric acid, and we need to find the concentration of PO43 minus ions in the solution. So again, we have to understand what is happening when the H3PO4 is dissolved in the water. So we have our reactions for the polyprotic acid. And in this case, we unfortunately, unlike in the previous problem, we cannot ignore these second and third reactions, because the PO43 minus concentration is yielded only by the third reaction. So we have to work with all three in this problem. So since the third one is the most important one in this case because it produces the PO43 minus, let's start off by drawing the equilibrium equation for this third reaction. So the Ka3 equals the products multiplied by each other, the H3O plus times the PO43 minus concentrations, over the reactants, the HPO42 minus, again ignore the water. And then we plug in what we know for these concentrations. At least we know some of the initials. From the previous problem, we know that most of the H3O plus, or at least the concentration of H3O plus that matters, is only produced by the first reaction because Ka1 is so much larger than the K2 and K3 that these two other ones don't really matter when influencing the concentration of H3O plus. So essentially we can use the H3O plus concentration we calculated from the first problem and plug it in here, and that was 0.170 molar. And that will be our initial H3O plus concentration before this reaction goes through. And we do not know the concentration of PO43 minus, so we'll label that as X. And since H3O plus and PO43 minus are produced in a 1-to-1 ratio, we'll say 0.170 plus X, just that extra H3O plus produced by this third reaction. Although this X doesn't really matter, this plus X right here, and will be eventually crossed out later on, because the Ka3 for this reaction is so small that the X plus X here doesn't make a difference to that 0.170. It's just too small. The problem is, though, we do not know the concentration of HPO42 minus, the initial concentration of that, and that we need to figure out the concentration of PO43 minus. We need that initial HPO42 minus concentration. So how do we obtain this concentration of HPO42 minus that was produced by the second reaction that will be used up in the third reaction? Well, we have to go through the first reaction, the second reaction, to get the concentration of HPO42 minus. So this is what we do. We know that in the first reaction, based on the previous problem, the first reaction produced 0.170 molar of H3O plus. And therefore, it also produced 0.170 molar of H2PO4 minus. This is because the H3O plus and the H2PO4 minus are in a 1-to-1 ratio, so an equal concentration of both are produced. Now this H2PO4 minus is actually going to be used up in the second reaction because we can see it goes and gets used up here to produce this HPO42 minus, whose concentration we're trying to find. So in the second reaction, in order to find the concentration of HPO4 produced by the second reaction, we need to draw the equilibrium equation for the second reaction. So the Ka2, which is 6.3 times 10 to the negative 8th, equals the product concentrations multiplied on top, so the H3O plus times the H3O4 plus, HPO4 over the reactant concentration, which is H2PO4 right here. And in this case, we know that from the first reaction, we got 0.170 molar of H2PO4 that was used up here. So we can put this H2PO4 concentration to 0.170 molar right for this H2PO4 concentration. So 0.170 here on the bottom. And we do not put minus X right here, let's say, because frankly, so little of this H2PO4 is actually dissociated because this initial concentration of H2PO4 right here is 1.70, which is more than 100 times greater than the Ka2 for this second equation, which is very small, 6.3 times 10 to the negative 8th. So the minus X here on the bottom doesn't matter. And also we can put the concentration of H3O plus that is already present in the solution. And we know from the first reaction we got 0.170 molar of this H3O plus. And we can put this right here. We do not need to put a plus X to this H3O plus concentration on top because, again, these other reactions contribute so little H3O plus that they make no difference. The H3O plus concentration essentially remains constant in the solution, like for all three. So it remains 0.170. And based on this, it becomes rather simple. We just cancel out the 0.170, 0.170, that equals 1. So X would equal 6.3 times 10 to the negative 8th. So 6.3 times 10 to the negative 8th molar of HPO4 is produced by the second reaction. Now that we know how much HPO4 is present in the solution, we can then figure out the concentration of PO4 that is produced. So again, we return to this Ka3 equation where we try to find the HPO4 concentration on the bottom. We know now that it is 6.3 times 10 to the negative 8th. So the Ka3 equals the 0.170 plus X on the top, this H3O plus whatever was newly added by this reaction, times X, which was the concentration of PO4 over this concentration of HPO4 because HPO4 is a reactant. So it's 6.3 times 10 to the negative 8th minus X, whatever portion of it dissociated. And for every X of that HPO4 that's associated, we get an X of this and an X of this. So plus X and X. However, again, like for the other reactions, we don't need this plus X because the 0.170 molar H3O plus concentration remains essentially constant for all three reactions. So we just multiply 0.170 by X and we take out this plus X. And on the bottom, we do not need this minus X because the initial concentration of HPO4 which is 6.3 times 10 to the negative 8th, is more than 100 times greater than the Ka3 for this third reaction. The Ka3 7.1 times 10 to the negative 13th, that's 5 orders of magnitude greater. So little of this HPO4 dissociates that its concentration virtually remains constant. So we can just ignore this minus X and put the 6.3 times 10 to the negative 8th on the bottom. And now we can simply solve. We know that this Ka3 is 7.1 times 10 to the negative 13th, which equals 0.170x over 6.3 times 10 to the negative 8th. We just solve for x. And in the end, after solving this, we get the x to be 2.63 times 10 to the negative 18 molar of PO4 ion. So you can see that's very little of this ion is actually produced. But we needed to find how much at least is produced. So using some of our approximations and some of our strategies, we could find the PO4 concentration for this polyprotic acid, the anion concentration in the third reaction. Part 6, Base Ionization and Strength. So in this video, we will be primarily focusing on Bronsted-Lowry bases. So a Bronsted-Lowry base is any substance that takes in these H plus ions in the solution. So you can see that the base, by taking up these H plus ions, it lowers their amount in the solution because they're all taken up by this base. And this raises the pH of the solution because there's less H plus floating around freely. I mean, it's in the form of a hydronium ion, and since there are less of these hydronium ions because the H plus is taken away, the pH of the solution goes up. However, again, like with the acids, this reaction is not representative of what actually happens when a base, the Bronsted-Lowry base, dissolves in water. What happens is that when this base dissociates, you see the A- is the common notation for the Bronsted-Lowry base. The A- would take an H from this H2O, because it's in H2O. It takes an H, and the H2O is only left with OH- because it lost the H. And now the A- gained an H to make HA. So the actual reaction of a Bronsted-Lowry base in water is A- plus H2O, and that would yield OH- and HA. And the OH- here is a hydroxide ion, and this is pretty strong base on its own. That's why this thing can be called a base, because it takes the H's in and produces the OH-, which also takes H's in. But for your purposes, just know that this is the base, the Bronsted-Lowry base, and this is the reaction. I would also like to mention that these Bronsted-Lowry bases are typically drawn as negative anions. This is because they take in the positive H+, and because the negative attracts positive, the base is very effective at taking these H pluses from the water and to make the solution basic. So how do we actually determine the strength of this A- base? Previously, we determined the strength of the acid by calculating the concentration of H plus it produced. Well, the concentration of the hydronium ions it produced, actually. However, there are no hydronium ions. There are none of these H3O plus ions here in this reaction. Instead, we have this ion right here, the hydroxide ion, which indicates how basic a solution is. And we can use the concentration of the OH- ion produced to determine the strength of the Bronsted-Lowry base. So again, in order to determine the strength of this Bronsted-Lowry base, we can draw its equilibrium equation, where the Kc, the equilibrium constant, equals to the concentration of the acid, well, this product right here, HA, times the concentration of the OH-, the other product, over the concentration of the A- and the concentration of the water. This is at equilibrium. This is once this reaction does its job, and when each of these concentrations become constant, we can draw this equation. However, so you can see the products on top and the reactants on the bottom. However, again, we do not need the concentration of water because there's so much water that its concentration essentially does not change, and it remains constant. So we can multiply it by the other constant, Kc, constant times constant, and that yields us another constant for this equilibrium equation. And in this case, the constant is called Kb, the base ionization constant. Remember Ka, the acid ionization constant? Well, this is its, you can say brother or sister. This is the Kb, the base ionization constant. And here we can see our base on the bottom, its concentration, and the concentration of the products multiplied by each other on the top. And these are the concentrations at the equilibrium. Once this reaction already passed through, and these concentrations become constant in the end of the reaction. And how can we measure the strength of this base? Well, typically we would see that the higher the OH-, the stronger the base. You can also see that the higher this OH- concentration becomes, the higher the Kb, indicating a stronger base. Remember that when the Ka was higher for an acid, we saw that the acid was stronger. Well, here when the Kb is higher for a base, the base is stronger. So you can see the OH-, if it's higher, then the pH is higher, and the solution becomes more basic. Part 7. Bases and pH. So as previously stated, in order to find out how basic a solution is, we typically need to know its pH. The higher the pH, the more basic the solution is. And as you can see, if it's above 7, between 7 and 14, it's basic. Well, 14 is also basic. And if it's below 7, then the solution is acidic. And at 7, it's neutral. So we need to find the pH, and for basic solution, it would be above 7. However, how do we actually find the pH calculation-wise? We know that the pH formula is negative log of the concentration of hydronium ion, H3O+, which equals the pH. But in this equation, in this reaction, for the base, we only have these OH- ions that were produced. So how do we exactly get the pH if we only have OH- ion concentrations and not the concentrations of H3O+? Well, here's a simple rule that you can memorize to know how to convert between the OH- concentration and the H3O+ concentration. At room temperature, the product of the concentration of H3O+ and the OH- concentration is always equal to 1 times 10 to the negative 14th in water. And this 1 times 10 to the negative 14th does not change at that certain temperature. And essentially, unless indicated, always assume that the product of the concentration of OH- and H3O+ is going to be 1 times 10 to the negative 14. It's just a rule that you have to memorize. And these concentrations, however, the OH- and the H3O+, can change, but this 1 times 10 to the negative 14 never changes. So if the H3O+ rises, then the OH- has to go down. Or if the H3O+ gets lower, then the OH- has to go up, because this product right here, 1 times 10 to the negative 14, never changes. And from this rule, we can obtain the concentration of H3O+, knowing the concentration of OH- from the base, so that we could figure out the pH. So we would take 1 times 10 to the negative 14 here, divided it by the OH- here, divided by OH- to find the concentration of H3O+, this concentration. So if we divide this by that, we find the H3O+ concentration. And once we get this H3O+ concentration, well, then we can easily find the pH by plugging it into our negative log H3O+ formula, and we'll have the pH, knowing only the concentration of OH- produced by our base. However, if you do not want to convert the concentration of OH- to the concentration of H3O+ to determine the pH, because that can be a bit time consuming, then you can take a shortcut, and I'll show you how. Some people prefer this method, some people don't. Personally, I prefer this method, but it's ultimately your choice. So there's a formula that says POH plus pH equals 14. Now we know that the P here stands for negative log of whatever's here. So essentially this formula is saying that the negative log of this OH- POH plus the negative log of this H, but in water it's H3O+, equals 14. So we can see that from this formula we can find this pH, but we have to calculate the POH. And that's very simple, because you know that the POH is just the negative log of this OH- concentration. And then all you have to do is subtract that from 14 to get this pH. So 14 minus the POH equals the pH. 14 minus this negative log of OH- will get you the negative log of H3O+, and that's the pH. So it's simple. Basically, as soon as you get this OH- concentration, all you have to do is get the negative log of it and just subtract it from 14 to get the pH. So this formula is a pretty fast shortcut that you can take to find the pH from the concentration of OH-. Pretty direct. Part 8. Determining base ionization, ion concentrations, and pH. So in order to find the concentrations of the products of a base reaction, the process is very similar to that of an acid reaction. Furthermore, we can also use the small number approximation. I will give an example problem and show you how to solve these problems. So let's say that we have 2 molar of ammonia, NH3, which is a base, that dissolves in water. Ammonia has a Kb base ionization constant of 1.8 times 10 to the negative fifth. And we need to find the pH of this solution. So how can we find the pH of the solution? Well, we need the concentration of OH minuses produced by this base to find the pH of the solution. So let's see what happens when ammonia actually dissolves in water. The ammonia, right here, takes an H from the H2O and becomes NH4+. And it leaves the H2O with OH-, our hydroxide ion. And by finding the concentration of these hydroxide ions, we can easily then find the pH. So how can we find the concentration of these hydroxide ions? Well, again, like for our acid problems, we have to draw an equilibrium equation for this reaction. We have the Kb, which is the base ionization constant, which equals to the product concentrations multiplied by each other, NH4+, and the OH- concentrations here. And the base concentration is on the bottom, the NH3. And again, remember, we do not include water at all, because the concentration of water always remains constant. We don't care about it. And this Kb, this equation, is when this reaction has reached the equilibrium. This means that the NH3, NH4+, and OH- concentrations are constant at this point because the reaction has reached its equilibrium. So let's substitute the values that we know into these various variables so that we can solve for the concentration of OH- to find our pH. So we know that the Kb is 1.8 times 10 to the negative fifth, as given above. And our initial concentration of NH3, the ammonia, is 2 molar, so we can put the 2 molar right here. And we do not know the concentration of NH4+ or the OH-. Furthermore, the 1.8 times 10 to the negative fifth equals 2. We can say this x times x on top, and the 2 minus x, because we do not know the final concentration of this NH3. And this equation is once the reaction is for when the reaction actually proceeds. So this NH3 concentration at the bottom actually changes, and so we represent it as 2 minus x. And remember that the NH3 here is in a 1-to-1 ratio to the NH4+ and the OH-. So for every x of this NH3 that reacted, an x amount of NH4+ is produced and an x amount of OH- is produced on top. So now we need to solve for the x in order to find the concentration of OH-. We take the 1.8 times 10 to the negative fifth, and we can take out this minus x right here. Why is that? This is because of our small number approximation, similarly to the acid problems. This is because the 2 molar initial concentration of NH3 is definitely more than 100 times greater than its Kb, 1.8 times 10 to the negative fifth. And that basically means that so little of this NH3 actually dissolves, reacts, that this minus x, this amount that reacted, essentially does not change the concentration, the initial concentration of NH3, because the initial concentration of NH3 is so much greater than its ionization constant. So we can ignore this minus x on the bottom because it doesn't change the bottom value, really. Now we can multiply this 2 by 1.8 times 10 to the negative fifth to get 3.6 times 10 to the negative fifth, which equals our x squared. We can take then the square root of this value, 3.6 times 10 to the negative fifth, square root of that, and that will be 0.006 molar. That will equal the x. And this 0.006 molar is equal to the concentration OH- once the reaction has reached equilibrium. So the OH- here, that will be the 0.006 molar. And now all we have to do is convert this concentration of OH- to the pH. So we can use that second method I taught you in the previous section, and we can take the negative log of this OH- of this 0.006 molar, negative log of that, and we will get 2.2. And we subtract this 2.2 from 14 to get our pH, which is 11.8. So effectively we just found the pH of this 2 molar ammonia solution that was in the water. Part 9. Acid-base salts. So sometimes there are certain salts that are acidic and certain salts that are basic. We call them either acidic salts or basic salts. So why is that? It's because a salt, we know, is a compound. It's an ionic compound. It has a positive part and a negative part, the cation and the positively charged cation and the negatively charged anion. And these combine to make the salt. For example, NaCl, the Na is the cation, the Cl minus is the anion, and they combine to make NaCl salt. Here's another example, magnesium 2 plus and sulfate 2 minus. This is the cation and this is the anion, and they combine to make the salt MgSO4. So a salt is essentially a cation plus an anion making this substance. Sometimes salts can either have an acidic cation or a basic anion. And the strengths of these, let's say one's acidic, one's basic, they basically compete. So let's say if the cation is acidic and the anion is basic, whichever one's like, if the anion is more basic than the cation is acidic, then the salt is basic. Or if the cation is more acidic than the anion is basic, then the salt is acidic. And when the salt, let's say, dissolves, if there's more of the basic substance, or the basic substance stronger, then the solution will be basic. For example, the NaCN salt is a basic salt because the Cn minus part of it, the anion part of it, is basic, while the Na plus part of it, the cation part, is neutral. So neutral plus basic is basic. So NaCN is a basic salt. Another example is NH4Cl. This ammonium chloride salt, the NH4 is acidic, the cation is acidic, and the anion Cl minus is neutral. So acidic plus neutral is acidic. NH4Cl is acidic. The salt makes an acidic solution. And finally, we have NaCl, and that's a neutral salt because obviously you've tasted salt before, and I don't think you've tasted acidic salt. It's neutral substance because the Na plus cation is neutral and the Cl minus anion is neutral. So when they both combine, neutral plus neutral gives us a neutral solution. However, this does not explain how to predict whether a salt is basic or acidic, and that's what I'm going to do right now. So in order to figure out whether a salt is acidic or basic or neutral, I'll give you a quick rule that you can use to know whether it's acidic or neutral or basic. So a salt is made out of a positive cation and a negative anion. Essentially, the cation can only be acidic or neutral. It cannot be basic. And the anion can only be basic or neutral. It cannot be acidic. But why is that? It's because the cation, because it's positive, it cannot really take any more new H pluses, positive H pluses, because positives repel positives. Instead, it has an easier time giving away H pluses because a positive repels a positive. On the other hand, the anion is good at taking in H pluses, and therefore could be a base because its negative charge and H plus is a positive charge and they attract each other. So cations are either acidic or neutral, and anions are either basic or neutral. So let's apply this rule to the following problem and see how we can determine whether a salt is acidic or basic. So in this problem we have NH4Cl, and we need to determine whether it is an acidic, neutral, or basic salt. The way we do that is we look at the ions present in the salt. There are only two. There's the NH4 plus cation, and then there is the Cl minus anion. And now we know from our first rule that the cation can either be acidic or neutral, and the anion can either be basic or neutral. And we need to figure out which of these two and which of these two are both of these ions. So the way we do that is we analyze the conjugate relationships in these ions. We need to see which substance could have produced these ions to see whether they are acidic, basic, or neutral. And the way we do that is for this cation, since it could be acidic, but it can't be basic, but it could be acidic, we need to find the conjugate base that produced this cation. And knowing the strength of that conjugate base, we could figure out the strength of this cation, indeed, whether it is acidic or neutral. And the conjugate base of NH4 plus is NH3, because the conjugate base and the conjugate acid only differ by one H plus. So in this case, the NH3, it's a conjugate base of NH4 plus, takes in an H plus and becomes NH4 plus. And we know from other acid-base chapters that there is a relationship between the conjugate base and its conjugate acid. And that basically the relationship states that if this, let's say, base is weak, then the acid is strong, or if this base is strong, then the acid is weak. So in this case, NH3, ammonia, is a weak base. Why is that? It's because it is not in our list of strong bases. So therefore we can say that it's a weak base. And because it is a weak base, then this NH4 plus is pretty acidic, let's just say. It's acidic. So therefore, the conjugate acid of a weak base is acidic. And in this case, the NH4 plus is going to be acidic. So now we know that the NH4 plus is acidic. And now let's see whether the Cl minus is basic or neutral. Again, we take its conjugate. In this case, since it could be basic, we take the conjugate acid of the Cl minus. For example, here, since this could be acidic, we could take its conjugate base. Since this is could be basic, we take its conjugate acid. And the conjugate acid of Cl minus is HCl, because it releases one H plus and then the Cl minus results. They only differ by one H plus. And again, the HCl in this case is actually a very strong acid. And it is in our list of strong acids. That's how we know it's a strong acid. While the Cl minus is a super weak neutral conjugate base, because the HCl is so strong that most of the reaction is essentially this HCl dissociated into H plus and Cl minus, and very little of this reaction goes in the reverse. So the Cl minus attracts very little H pluses back, and making it essentially a neutral substance, because this is such a strong acid. So if the conjugate acid is super strong, the conjugate base of that conjugate acid is super weak and therefore neutral. So now we know that the NH4 plus is acidic, and we know that the Cl minus is neutral. And because of that, we can say that acidic plus neutral is acidic. Therefore, the NH4Cl is acidic. So what we do, just to recap, we take either the conjugate base or acid of these substances. For the cation, we take its conjugate base, because the cation could be acidic, so we take its opposite, the conjugate base. And for the anion, we take its conjugate acid, because the cation could be, the anion, in this case, could be basic, and therefore we take its opposite, the conjugate acid. And we use these to determine the strength of both of these ions in these reactions. And that is how we determine whether a salt is acidic or basic. So I just want to do another problem here, another example, just to drill this concept in. So let's see, is NaCN an acidic, basic, or neutral salt? Well, first we take the cation, the Na+, and cations can either be acidic or neutral, and we need to find out which one. So again, we take the conjugate base of this potentially acidic cation. And the conjugate base of Na+ is NaOH. It is the only type of base that can produce Na+. Yes, they don't differ by single H, but this is the only base that can produce Na+, and we need to check the relative strength to see whether Na+ is acidic or neutral. And because the NaOH is such a super strong base, it is in our list of strong bases, this Na+ is then a weak, super weak conjugate acid, because the strong base has a very, very, very weak conjugate acid. It is so weak that it is neutral. So the Na+ is neutral. Then we take the Cn- part, the anion, and we determine whether it's basic or neutral, because anions can either be basic or neutral. And again, we take In this case, since it could potentially be basic, we take its conjugate acid to see their relationship in strength. So the conjugate acid of Cn- is HCN, and this HCN releases 1H plus and the Cn-. And HCN is a weak acid because, again, it is not in our list of strong acids, so it must be weak. So if it's a weak acid, that means its conjugate base is basic. It's fairly strong then. Well, not exactly super strong, but decently strong to be basic. So the Cn- is basic because it has a very weak conjugate acid. So now we know the Cn- anion is basic. So because the Na plus is neutral and the Cn- is basic, the whole substance is basic. So NaCN is basic. And in general, I just want to comment that the Na plus cation, it is always neutral. Always. Just remember that Na plus is always neutral because you'll be given a lot of problems with Na plus. And if you remember that Na plus is neutral, that'll basically save you half the job. Part 10. Finding acid-base salt pH. Now that we know how to determine whether a salt is acidic or basic, we need to know how to determine the pH, or how acidic or basic the salt is. Well, at least a number that corresponds to this. And in order to do so, we have to keep one thing in mind. Whenever we dissolve a salt in water, if that salt is soluble, and you can check your solubility table to see if it's soluble, if it is soluble, we treat the salt as if it completely dissociates into its ions. Essentially, only these Na plus and Cn- ions are present in the solution, and almost all of it dissociates into these ions. So we do not need to know the Kc of the salt. We do not need to know its equilibrium dissociation constant. All we have to keep in mind is that if it's soluble, let's say if 5 molar of this salt is dissolved, then 5 molar of Na plus is produced and 5 molar of Cn- is produced. It's just that. And then all we have to do after that is we only care about these ions whenever we're trying to find whether the pH of these solutions. We do not care about, let's say, the equilibrium constant of the salt because it essentially completely dissociates. And that's what we have to know. So if there's 5 molar of the salt, there's going to be 5 molar of Na plus and 5 molar of Cn-, and then we can ignore anything dealing with the salt later on. All we have to do is then see how these ions make the solutions basic or acidic. So let's say that we have 3 molar of NaCN, the salt, dissolved in water. The Kb for Cn- is 2 times 10 to the negative fifth, and we need to find the pH of this solution. So our first step would be to know what is happening when NaCN dissolves. The NaCN dissociates into the Na plus ion and the Cn- ion. And this dissociation is essentially complete. Since this is a soluble salt, most of it is present in the form of Na plus and Cn- ions, and almost nothing of this is left, the solid portion. So now that we know that if 3 molar of this salt is dissolved, then 3 molar of the Na plus and 3 molar of the Cn- are produced because they're in a 1-to-1 ratio. And we also know, based on our previous example, that the Na plus is always neutral and that the Cn- is basic because we can determine that using its conjugate acid. Since the HCN, its conjugate acid, is a weak acid, then this conjugate base of that acid is pretty basic. So Cn- is basic. And that means that this solution is going to be basic. And we only need to know how to solve for the concentration of OH- because this Na plus does not change anything. So all that matters here is the Cn- ion. And what happens when the Cn- ion is released into the solution by the NaCN? Well, this is what happens. The Cn- combines with water. It takes an H away from water, produces HCN, and leaves OH- because it took the H away from water to produce OH-. And this becomes a simple base problem where we have to figure out the concentration of the concentration of OH minus ions produced by 3 molar of Cn minus, so that then we could figure out the pH. And we write the equilibrium equation for the Cn minus ion, because we don't care about this, we only care about this active ion that actually makes the solution basic. So the Kb equals the HCN times the OH minus, the products, the concentration of the products multiplied, over the concentration of the reactant, the Cn minus. And let's substitute the values. So the Kb for Cn minus is given 2 times 10 to the negative fifth, and this equals the initial concentration of Cn minus right here, the 3 beneath. 3 molar of NaCN produces 3 molar of Cn minus, so we draw the 3 for the concentration of Cn minus on the bottom. And remember, we don't include this minus x right here because the initial concentration of Cn minus is more than 100 times greater than its K of 2 times 10 to the negative fifth. This is more than 100 times greater than 2 times 10 to the negative fifth. So little, there's such a little change of the concentration of Cn minus that it doesn't matter really. And on the top we have the x squared, because x times x is x squared on the top. And now we just have to solve for x. So we multiply the 3 by 2 times 10 to the negative fifth to get 6 times 10 to the negative fifth, and that will equal x squared. Then we square root the 6 times 10 to the negative fifth to get 0.0077 molar of OH minus that the Cn minus produces. And that essentially this salt produced as a result of releasing the Cn minus, which then went on to produce this OH minus concentration that actually changed the pH. And now we can figure out the pH pretty easily. We just take the negative log of this 0.0077, and that would be 2.11, and we subtract it from the 14, value 14 minus 2.11, and that will give us a pH of 11.89. So these problems are actually relatively simple in that all you have to know is that the ions matter, not the salt itself, the concentrations of the ions matter, and how these ions interact, not like the overall salt. So we only care about the Cn minus and the Na plus, and if the Na plus is neutral, we don't really care about it also. So essentially then it's just the Cn minus doing the job. So it's these active ions that do the job, and we calculate the pH from their activity. Sometimes both ions can be acidic, sometimes one ion can be acidic and one ion can be basic, and then we just calculate their the concentration of H plus and OH minus produced by both of them and see which one outweighs the other, and then we can calculate the pH. But you can find these problems in the textbook and probably other problems online regarding these acid-base salts. However, sometimes these acid-base salt problems can get a little bit more tricky. So let's take the problem we had last time and I'll show you how it can get trickier. So we have the 3 molar of NaCN dissolved in water, and instead of giving us the Kb of the Cn minus, this problem gives us the Ka for HCN, the conjugate acid of Cn minus. And that Ka is 5 times 10 to the negative 10th. So we need to find the pH of the solution. Now in this solution we know that this 3 molar of NaCN dissociates completely and produces 3 molar of Cn minus. And we could easily find the pH of this 3 molar Cn minus, and therefore the pH of the solution, if we had the Kb value for Cn minus. But in this case we have only the Ka value for its conjugate acid, HCN. So how can we figure out the Kb from the given Ka of this conjugate acid? Well, we first have to understand a formula converting the Ka to Kb. Essentially, when this conjugate acid of Cn- dissociates in water, this is its reaction. It gives the H to water and it produces H3O plus and a Cn- because the H is lost and the Cn- is left. So in this case, the Ka for HCN represents this reaction, where the products are Cn- and H3O plus because this acid dissociates. On the other hand, this Cn- that's produced in this reaction can actually go in the reverse direction. However, it doesn't exactly, sometimes it can combine with these hydronium ions, the H3O+, but it also can do this. This Cn- can then react with water, like in this case, and go backwards, where the Cn- takes the H from water to produce OH- and HCN, because the Cn- gains the H. So we go in this loop. So we produce the Cn- and the Cn- reacts back to form the original HCN. From HCN to Cn-, from Cn- back to HCN. And in this case, the second case, the backwards reaction here is the Kb for Cn-, because the Cn- takes an H and produces OH- and HCN. So that's the Kb for Cn-. And we also know that the product of the concentration of H3O+ and the OH- in any solution at a certain temperature, in this case room temperature, is equal to 1 times 10 to the negative 14th. So the product of H3O+ and this OH- has to equal 1 times 10 to the negative 14th. And we also know that this Ka here, the one in the forward reaction, it can be used to represent to what extent this acid produces H3O+. And this Kb in this reverse reaction can be used to show to what extent does this Cn- produce OH-. So essentially, this Ka can be seen as a measure of the concentration of H3O+ produced, because it shows how much this acid will dissociate to produce H3O+. And this Kb can be used to show how much this acid dissociates to produce OH-. It can indirectly be used as a measure to show how much OH- is produced. And since the Ka and the Kb correspond to the H3O+ and the OH- respectively, they are proportionally corresponding to both of them, then we can write this equation where the Ka times the Kb also equals to 1 times 10 to the negative 14th, just like the H3O+ and the OH-, because both correspond to each of these. So Ka corresponds to H3O+ production, Kb corresponds to OH- production. You can actually play around with these equations and rearrange them in a way that shows that this formula is indeed correct, but I am not going to do that here. I'm just going to illustrate this basic concept where this Ka corresponds to the concentration of H3O+, the Kb corresponds to the concentration of OH-, and since H3O+ times OH- is equal to 1 times 10 to the negative 14th, therefore the Ka times the Kb is also equal to 1 times 10 to the negative 14th. Now that we know that there is this relationship between the Ka and the Kb, we can actually find the Kb for Cn- using the Ka for the HCN. So we know that the Ka for HCN is 5 times 10 to the negative 10th, and we do not know the Kb for Cn-, but we need to find it. And we know that their product, since they're conjugate acid and base, is equal to 1 times 10 to the negative 14th. Therefore, we can divide 1 times 10 to the negative 14th by the 5 times 10 to the negative 10th and find the Kb for Cn-. In this case, the answer will be 2 times 10 to the negative 5th for Cn-. And we can easily use this Kb, which is exactly the same one given in the previous problem, to calculate the pH in this solution. And I already did that in the last problem with this Kb, so that's pretty easy to do. And that is how you get the Kb from the Ka that is given of this conjugate acid. We need to find the Kb of this conjugate base. Part 11. Buffers. What are they? A buffer is a solution that resists changes in pH. If the pH tries to go up, the solution resists it. If the pH tries to go down, the solution also resists that. So a buffer is a solution that resists changes in pH. However, what is the mechanism behind this? How does this actually happen? I'll show you. Usually, buffers are solutions of a weak acid, so in this case HA is a weak acid, and a weak base, the weak conjugate base of that weak acid, so in this case represented by A-. So the weak acid and its weak conjugate base. And they're in roughly equal concentrations in the solution, roughly equal amounts. So the equation the reaction for this buffer is going to be HA plus H2O gives an H to this H2O and it produces H3O plus and A minus. So this is how these two, the conjugate acid and the conjugate base, both are weak, are related to each other. And the concentration of, let's say, HA is 1 molar and the concentration of A minus, let's say, is also 1 molar because they're in roughly equal amounts. Many people make the mistake thinking that a buffer can be made essentially when you only add HA and then it dissociates to produce some A minus. But that is not the case because if HA is such a weak acid, then so little A minus is produced that it is essentially not a buffer. Instead, the way a buffer is produced is this way. Usually you have a separate vial of, let's say, HA, this weak conjugate acid, and a separate vial of its weak conjugate base, the A minus. There are roughly equal amounts of both. So yes, this HA dissociates in its own vial to produce some A minus, but it's essentially negligible because remember, this is a weak acid. It's so little A minus actually produced. And here this A minus also takes H's from the water to produce some HA, but very little, so little that it doesn't really matter. So we can say essentially that most of this is HA and most of this is A minus. In fact, there's so much of both that we can say almost all of it's HA and almost all of it's A minus. And then we take these vials and we pour them into our solution, into the water below. So the HA is poured in, the A minus is poured in, an equal amount of both. And now we have a roughly equal amount of HA and A minus. Yes, some of the HA might dissociate to produce some A minus. And some A minus might go the other way, taking some H's to produce HA again. But because both are weak, this does not really happen. These initial concentrations that we added essentially remain constant because they're very weak reactions going back and forth. And remember, they also go constantly back and forth. So they constantly replenish each other's concentration. And so the reactions are so little that this 1-to-1 ratio remains in the buffer essentially forever. So if you add this and this to the buffer, there's a 1-to-1 ratio as long as the solution remains untouched. And that's how a buffer is produced. It's not produced by simply adding HA or A minus to produce one or the other because very little of the other is actually produced. Instead, we add them separately and we add a large amount of both so that there's a large amount present. They're roughly in 1-to-1 concentrations and their concentrations don't change because there are already so much of them that the back and forth reactions don't really make a difference. So that is how a buffer is actually produced. So this buffer right here that we have, this HA and A minus buffer, its function is to resist changes in pH. And how it does this is by, when we add, let's say, a strong acid or a strong base, it prevents that strong acid or the strong base from changing the pH of the solution. And I'm going to show you an example right now illustrating how this type of buffer acts to prevent these pH changes from strong acids or strong bases. So let's say, for example, we have this buffer with an equal concentration of NH4 plus and NH3. We have 1 molar of NH4 plus, which is a weak acid, and 1 molar of its weak conjugate base, NH3. And then all of a sudden, we added 0.5 molar HCl to this 1-to-1 peaceful solution. We added this strong acid, 0.5 molar of HCl. So what happens to the solution? Does the pH change? How much does it change by? Well, we'll see what happens by checking how these reactions actually go in solution. So you know that because HCl is one of our strong acids, it completely dissociates into H plus and Cl minus, completely. Essentially, there's only H plus from this HCl and only Cl minus, and none of this original HCl is left. So now let's see what these ions do once they are released into the solution. This H plus ion is what matters because the Cl minus ion is neutral. We do not really care about what it does to this buffer because frankly, it doesn't matter. It's neutral. It's the conjugate base of a super strong acid, so it's neutral and doesn't have any effect. So the H plus is what really has the effect. So when the HCl releases this H plus into water, there are two things that this H plus could bind to. It could either bind to water to produce this hydronium ion, or it could either bind to the weak base that's already present, this NH3, to produce NH4+. In the case of this buffer, it binds to NH3 and not to H2O. And why is that? Well, that's because NH3 is a much stronger base than water, because water is neutral and NH3 is basic. So NH3 attracts these H pluses better, so all of these H pluses go to all of the available NH3s. They essentially, all of the H plus, as long as there's enough NH3, are used up by this NH3 to produce NH4+. So originally, basically, we had 1 molar of NH4+ and we had 1 molar of NH3. And while they were present, they were obviously reacting back and forth. There was the NH4+, giving H pluses to water to make H3O+ and then H3, and the NH3 was going back, taking away the H pluses from water, or in this case the hydronium ion, and making more NH4+. But because, remember, the key here is that both are super weak. So because they are weak, these reactions don't really change their initial concentrations. This 1 molar and this 1 molar remains constant because they're going back and forth and in such little amounts that these 1 molar concentrations remain constant. Then, all of a sudden, we add HCl. And this HCl, this 0.5 molar of this HCl completely dissociates. So the 0.5 molar of HCl becomes 0 because there's no more HCl present in its original form. Instead, 0.5 molar of this H plus is added to the solution, and 0.5 molar of this Cl minus is added to the solution. Is released into the solution by the HCl. And all of this H plus, the 0.5 molar, as long as there's less H plus than the concentration of NH3, it goes to NH3. So this NH3 takes in this H plus and goes backwards and produces this NH4 plus. So in this reaction, this NH3 would take the H plus and produce NH4 plus. That's why I'm drawing it backwards. So if 0.5 molar of this H plus are taken in by NH3, there is no longer this 0.5 molar of H plus because it's completely taken up by NH3 because it is such a strong, NH3 tends to bind to all of these H pluses. So the NH3 concentration actually decreases by 0.5 molar because 0.5 molar of this NH3 binds to 0.5 molar of this H plus to produce an additional 0.5 molar of NH4 plus. So this concentration of NH3 decreases by 0.5 molar, and this concentration of NH4 plus increases by 0.5 molar. And this is all that happens when 0.5 molar of HCl is added. Now you might ask, whoa there, now we have, instead of 1-to-1 molar of NH4 plus and NH3, we have 1.5 molar of NH4 plus to 0.5 molar of NH3. That's a large change in the ratios. Will that change the pH by much? Well, the answer here again is because both of these are so weak. This is a weak acid and this is a weak base. Their change in concentrations does not really change the pH by much. Yes, because more NH4 plus now is present, the pH slightly decreases. But because it's such a weak acid, even though there's more of it present, it doesn't really lower the pH by much as the HCl by itself would if it was allowed to act by itself without any of these present. But because this NH3 absorbed these H plus ions from Cl minus to make more NH4 plus, and this NH4 plus is not that good at releasing these H ions, the change in pH is much lower. It doesn't change as much because there are less of these free H plus ions. Because the NH3 took them up, made more NH4 plus, and this NH4 plus is much worse at releasing these H pluses than HCl was. And remember, the HCl got used up. All of it dissociated, and all of these H pluses went to the NH3, got taken in, and it produced more of this NH4 plus. And that's how this buffer acted. It prevented a significant change in the pH by taking up the H pluses added by the strong acid, making more of that weak acid, which is very bad at releasing these H plus ions, and therefore the pH doesn't change by much. Because remember, even though the ratio of this to this is changed in this reaction is so weak, because both components are weak, that the pH changes very little if we only have the NH4 plus and the NH3 concentrations change, and this HCl is used up. I would also like to point out that, let's say in this case we only added 0.5 molar HCl, which is less HCl, less concentration than, let's say, this NH3. Let's say instead we added like 1.5 molar of HCl, or a high concentration with an NH3. What would happen is that all of the H pluses, as long as there's enough NH3, would get used up. So let's say, in this case, since we only have 1 molar of NH3, then 1 molar of the H pluses would get used up first by the NH3. And then the remaining H pluses would then be taken up by water to form hydronium ions. I'm just clarifying this because you don't get the impression that once these H pluses bind to its NH4 plus, the additional H pluses go nowhere. No, then they bind to the water. But this happens only after the NH3 uses up these the H pluses bind to all available NH3s, and then they start binding to water. It's like an hierarchy here. So let's say that instead of adding a strong acid like that 0.5 molar of HCl to this buffer of 1 molar NH4 plus to 1 molar NH3, we add a strong base instead, 0.5 molar of NaOH, sodium hydroxide, a very strong base. And we add it to this 1 molar NH4 plus solution and 1 molar NH3 solution. They're combined together, there's a buffer. And let's see the effects on the pH and how this buffer resists the changes in pH that NaOH would typically cause by itself. So when NaOH dissociates like HCl, it dissociates completely. Essentially, almost none of this remains, and most of this and this instead is produced. Almost all of it dissociates into Na plus and OH minus. And since we know that Na plus is a neutral ion, the only ion here that actually has an effect is the OH minus, the hydroxide ion, which is a very basic ion because it's negative and it can pull these positive H pluses to itself to make water. And that is exactly what happens. This OH minus goes into the solution and reacts with the NH4 plus that is already present. And the NH4 plus, it takes away the H pluses from the NH4 plus. It pulls them away to itself. So no matter what the dissociation constant on this NH4 plus is, the OH minus does not care really. It is so strong that it pulls as many H pluses as many OH minuses can actually bind to these H pluses. So if there's one OH minus, it'll pull off one H plus. If there's 10,000 OH minuses, it'll pull off 10,000 H pluses. If there's 0.5 molar OH minuses, it's going to pull off 0.5 molar of H pluses because it's so strong that it doesn't matter that this is a weak acid. It will pull off these H pluses no matter what. And in this case, that yields more NH3 because the NH4 plus lost an H formed NH3. And the OH minus, because it combined with the additional H pluses, formed H2O. So initially we had 1 molar of NH4 plus and 1 molar of NH3. Then what happened was that we added the NaOH. So the NaOH was initially 0.5 molar, but it dissociated completely, so it was then 0 molar. Because, technically we can still say it's 0.5 molar present, but not in its original form. There's none in its original form of NaOH. And this yielded 0.5 molar of Na plus and 0.5 molar of OH minus. And all of this OH minus then goes and reacts with NH4 plus, because all of this, as much OH minus as there is NH4 plus. So as long as there's less OH minus than NH4 plus, this OH minus can pull off as many H pluses as it wants, as it can. So when 0.5 molar of OH minus reacts with 1 molar of NH4 plus, 0.5 molar of this NH4 plus combines with 0.5 molar of this OH minus. It doesn't combine actually, it gives, so the 0.5 molar of this NH4 plus gives 0.5 molar H plus to 0.5 molar OH minus to form water. And because half of this, essentially, 0.5 molar of this gave, 0.5 molar of NH4 plus gave H pluses to OH minus, the concentration of NH4 plus decreases by 0.5 molar. And we only have the other portion of it left without the H, so there's 0.5 molar NH3 formed. So originally we had 1 molar of NH3, now there's an additional 0.5 molar formed to it. So, and the concentration of water does not matter, remember that. So, because of this, our change in concentration of NH4 plus, it gave us a concentration, final concentration of NH4 plus after this base was added and these OH minuses took in the necessary H pluses from the NH4 plus. We get 0.5 molar of NH4 plus at the end to 1.5 molar of NH3 at the end. So previously we had 1 molar of NH4 plus to 1 molar of NH3. Now we have 0.5 molar of NH4 plus to 1.5 molar of NH3. And again, this does not change the pH of the solution by much, because remember, both are so weak that even though their concentrations changed by a lot, and the pH did become slightly higher because there's more of this basic NH3, it didn't become higher by much, because again, these are very weak substances and don't contribute to much pH change, even though their concentration changes by a lot. So how did this essentially, let's just to recap, how did this buffer add when the strong base was added? It used its weak acid to give as many H pluses necessary to satisfy all of these OH minuses. So these OH minuses were neutralized by the NH4 plus to form water, and water is neutral, doesn't change the pH. And as a result, more of this NH3 formed. But that doesn't really matter because this NH3 is much worse at being a base than NaOH, and doesn't change the pH as much as the NaOH would have changed if it were alone. So this buffer basically significantly weakened the pH change that this NaOH would have caused if it were by itself, by the production of more NH3 through the neutralization of OH minus, and the pH increased by a very, very, very small amount. I would also like to mention that the best ratio of the weak acid to the weak base, the conjugate acid to the conjugate base in the buffer, is 1:1. This is the most effective buffer. And why is that? Because frequently people say it's the most effective buffer, but they don't explain why. Well, this is because both sides are then equally equipped to deal with either additions of a strong acid or a strong base. Let's say we added 0.5 molar of HCl, a strong acid. Then the concentration of this weak base will decrease to 0.5, from 1 to 0.5, and the concentration of this weak acid will increase from 1 to 1.5, because 0.5 molar of this H plus from this HCl went to this NH3, got absorbed by it, and that produced the NH4 plus. And let's say if we had a 1:1 ratio again initially, and instead 0.5 molar NaOH was added. Well, in that case, the NH4 plus then gives 0.5 molar of H plus to 0.5 molar of OH minus to produce, and it's left with, and then there's 0.5 molar more NH3 because it lost 0.5 molar of H plus, and now we have a 0.5 to 1.5 ratio. Essentially, if we added the strong acid, then this side was equipped to deal with it, and if we added the strong base, then this side was equipped to deal with it. And in these cases, you can see that these sides were equally equipped. This side was equally equipped as this side to deal with, let's say, the strong acid in this case and the strong base in this case. And since a 1:1 buffer is equally equipped to deal with both strong acids and strong bases, it is most effective at resisting changes in pH either way, either up or down. Part 12. Finding buffer pH the hard way. So I'm going to show you an example here of how we can calculate the pH of buffers. Let's say we have, and this is the hard way of calculating the pH. So let's say we have a buffer with 1 molar NH4 plus concentration and a 1 molar NH3 concentration. The Ka of NH4 plus is 5.56 times 10 to the negative 10th, and the Kb of NH3 is 1.8 times 10 to the negative 5th, and we need to find the pH of this buffer. Here we can see that there is this weak conjugate acid, the NH4 plus, and then there is this weak conjugate base, the NH3, and they're in a 1-to-1 ratio. So before I start, I would like to show what exactly happens in this buffer when it reacts in the solution, so we could understand why I'm using this solution to find the concentration of H2O plus. So a lot of people make the mistake when calculating this H2O plus concentration that they think that because we have a lot of NH4 plus and a lot of NH3, that means some of this NH4 plus reacts to form H2O plus, and some of this NH3 reacts to form some OH minus, because this NH3 reacts with water to form some OH minus. Backwards. And they believe then that we have to first calculate the H2O plus concentration produced by the NH4 plus reacting this way, and the OH minus concentration produced by the NH3 reacting that way. And then we basically like see whether there's more OH minus or H3O plus and subtract them out, and whoever wins, like whoever has a greater concentration, basically decides the pH. So if there's more H2O plus than OH minus, then it's going to be acidic, or more OH minus than H2O plus, then it's going to be basic. Well, and like we subtract them out at the end and see how it goes, because this reaction goes one way, this reaction goes the other way, and then we gotta basically see how many of them neutralize each other, and whoever's left wins. That's not actually how these buffers behave. What actually happens is that this NH4 plus reacts to produce some H3O plus, and this H3O plus concentration remains constant. And then this NH3 reacts then separately with water to produce some OH minus, and that OH minus concentration remains constant. The produced H3O plus and the produced OH minus don't like react and the winner decides all. That's baloney. That doesn't happen. What actually happens is that the H2O plus and the OH minus concentrations remain constant. And why do they remain constant? Well, that's because, remember, the product of the H2O plus concentration and the OH minus concentration is equal to 1 times 10 to the negative 14th. So if there is, let's say, some constant amount of H2O plus produced, and then there's some constant amount of OH minus produced, their product is equal to 1 times 10 to the negative 14th. So we only have to find one of the concentrations, either the H3O plus concentration or the OH minus concentration, to find the pH. We do not need to find both, because both are already related in a way that makes like sense, in that their concentrations multiply to become 1 times 10 to the negative 14th. We do not need to like find the OH minus and the H3O plus and then put them in this competition to see what the pH is. This is because they're already constant. Once this is produced and once the OH minus is produced, they remain constant. They don't like combat with each other. So we only need to find, let's say, the H2O plus concentration to get the pH, or the OH minus concentration to get the pH. Either or. You don't have to find both. It doesn't make sense, because you get the same pH from both, because they're already constant. They don't change. So you get the same pH if you find the OH minus concentration, or if you get the H2O plus concentration. So the easier way in this case would be to find the H2O plus concentration, because I already drew the reaction of how it is produced. So the NH4 plus reacts with H2O, takes an H, gives an H to H2O to form H2O plus, and the NH3 is the remaining NH4 plus, since the H was lost, to form NH3. And these initial concentrations of the 1 molar NH4 plus and the 1 molar NH3 essentially remain constant, because these reactions are very small relative to these giant initial concentrations. So these giant initial concentrations essentially, although slightly, but they essentially don't change. Doesn't really matter. What matters though is how much of this H2O plus is produced. So we can draw the equilibrium equation for this equation to find the H2O plus produced, because we only need to calculate the H2O plus produced. We do not care about the OH minus. if you would like, you can switch this reaction, yeah? And then make NH3 react with water to form NH4 plus and OH minus, and draw the Kb for this with the NH4 plus times OH minus over NH3 on the bottom. But in this case, I'm doing the Ka because the NH4 plus is the reactant and it is acidic, so it's going to be the Ka. So NH4 because it's forming the H3O plus. So NH4 plus is on the bottom, NH3 and H3O plus are on the top. These are the products multiplied over the reactant. And now let's substitute what we know. We know that there is originally 1 molar of NH3. We know that some additional is produced in this reaction. We also know that there's an X amount of H3O plus. We don't know how much is actually produced. We know that an X amount of this 1 molar NH4 plus initial concentration reacts. So for every X of this NH4 plus that reacts, an X amount of NH3 and X amount of H3O plus is produced. So X and X right here. Plus X and X, because it's additional and they're in a 1-to-1 ratio. But again, we do not need this plus X nor this minus X on the bottom, because these 1 molar concentrations remain essentially constant even though the reaction goes through, because these reactions are so small. The only thing that matters is the additional H3O plus produced. So the Ka equals 1 times X over 1. We can cancel out the 1s, and the Ka, since it is 5.56 times 10 to the negative 10th, it would equal this X, because the 1s are cancelled out. So X equals 5.56 times 10 to the negative 10th. And that is the concentration of H3O plus in the solution. Now let's simply take the negative log of this concentration, and boom, we get the pH, 9.255 of the solution. So this is a basic buffer, and it resists changes in pH. So again, I would like to just emphasize again, because a lot of people make this mistake. They think, oh, we got to find the H2O plus concentration, and then we got to go backwards to find the OH minus concentration, and then we got to balance each other, both of them out in like this competition. Whoever cancels each other out, and whoever wins decides the pH. Nope, that's not how it works. The H2O plus concentration, once it is produced, remains constant, and the OH minus concentration, the other direction, once it is produced, remains constant. So all we have to do is find one of them, either the OH minus or the H2O plus, because they're always going to have to be in a certain like relationship where their product equals 1 times 10 to the negative 14. So we only have to find either H2O plus or OH minus to find the pH, since both of them are constant. And in this case, it's just easier to find the H2O plus. Part 13. Finding buffer pH the easy way. Now, on your exams and in some real-life applications, you need a faster method to find the buffer pH. This method comes in the form of the Henderson-Hasselbalch equation. This equation might seem complex at first. The equation states the logarithm of A minus the concentration of the conjugate base over the concentration of the weak conjugate acid minus the log of the Ka constant for this acid equals the pH of the buffer. And this equation seems fairly complex, but I'll explain how it was made and why it works. So to start off, we know that for any buffer, yes, we have our weak conjugate base and its weak conjugate acid mixed together in the solution. Now, these conjugate bases and acids might be mixed in different ratios. For example, in this case, there's a lot of this weak conjugate base and a little bit of this weak conjugate acid. On the other hand, in this case, there's a little bit of this weak conjugate base and a lot of this weak conjugate acid. So their ratios might change in different solutions, as can be seen here. And so would the pHs. The pH here is different from, let's say, the pH here. In this case, we have more of the base, so the pH is slightly higher. And in this case, we have more of the acid, so the pH is slightly lower. So, in order to find the pH of any of these solutions that are in different, let's say, ratios, we typically draw the Ka equilibrium equation for the acid dissociation. Because let's say our buffer equation looks like this: HA plus H2O makes A minus and H3O plus. We put these products on top of the reactant and we get this Ka. And then once we find the H3O plus concentration, then we can easily find the pH by plugging it into the negative log H3O plus equals pH. But wouldn't it be nicer if we could just get the pH automatically without plugging it in, without first finding the H2O plus concentration and then having to plug it into the negative log equation to find the pH? That's like 2 steps right there. Wouldn't it be nicer to just have a one-step equation? Well, that is exactly what our Henderson-Hasselbalch equation does. It combines these 2 steps into one equation. So you don't have to find first the H2O plus concentration and then use that to find the pH. All you have to do is know our initial weak base concentration and initial weak acid concentration, and know the Ka for this weak acid, which is typically given in the problem, and then we can just easily get the pH in one step, in one go, without having to do first this step, then that step. This is a one-step equation. So the way this equation was originally derived was basically when we draw the Ka, let's say right here, we drew the Ka for our buffer reaction on top. We get the products time over the reactants. So A minus plus X, because we don't know how much of this additional A minus was made, times X, because the additional amount of A minus that was made equals to the additional concentration of H2O plus that was added. So because they're in a 1-to-1 ratio. So for every X of this HA that dissociates, an X amount of additional A minus is added and an X amount of H2O plus is made, because originally there was virtually none of this H2O plus. But remember, our small number approximation dictates that if there are large concentrations of this weak acid and its weak conjugate base, then we can ignore the minus X and the plus X because they don't really change these giant concentrations, that even like this tiny addition wouldn't change such a big concentration. It's already too large to change essentially. And this usually happens when the initial concentration of the acid is more than 100 times greater than Ka, and that is the case for essentially almost all buffer problems, because typically we add a lot of A minus and a lot of HA so that the buffer could have like resistance to strong acids and strong bases. So we take out the plus X and the minus X on the bottom, and we get just the A minus and just the HA and this H2O plus, which you can label as X, but in this case, for convenience purposes and for showing how this equation is derived, I replace this X with the H2O plus concentration. Now the way we derive this equation is by first separating out the H2O plus. So now we have A minus over HA times H2O plus. We took this H2O plus and put it right here, for example. So now it's multiplied. Then we take this A minus and HA and put it on the side of the Ka. And here we did that. And we have to flip our fraction because we just shifted it to the other side of the equation. So now it's HA over A minus instead of A minus over HA. And this equals to H3O plus concentration. Now we know that if we take the negative log of this H2O plus concentration, that would be the pH. And that is exactly what we do here. The negative log of H2O plus, that's going to be the pH. But since we negative logged this side, we also have to take the negative log of this side. And that is exactly what we do here. Negative log of the Ka times the HA over A minus. And then it just comes down to a simple algebraic rule of logarithms, where we know that if there is a multiplication within the logarithm, it's technically like an addition. And then we distribute the negatives inside, and I mean, if you know your logarithm rules, you can see how this was derived basically. And now we take our negative log Ka, so this part, and we originally had a plus sign here basically in between, but now we can distribute the negative inside and get negative log HA over A minus, just to get the log distributed within both of these terms. And that would equal the pH, because the negative log of H2O plus is the same thing as pH. And then we can make this logarithm positive by flipping this fraction to A minus over HA instead of HA over A minus, and we get this side to be, this log to be positive, and we put it right here because it's a positive log, and then this minus log stays the same, minus log Ka equals the pH. And that is exactly our Henderson-Hasselbalch equation. So essentially the way this equation works is that for any initial concentration of A minus to HA, if we find out their initial concentrations in the solution, and we know that they really don't change, they essentially stay the same all the time, and we know the Ka for this HA, then we can get the pH in one go. So the problem gives us the concentration of A minus and the concentration of HA. We do not have to do this minus X plus X because they don't change. They are so weak, they really don't change because there are already such large concentrations of them inside. And all we have to do is know this ratio, and for that ratio we can get a certain pH. So let's say there's more A minus on the top and less HA on the bottom. Since there's more of the weak base on the top, this logarithm is going to be higher in value, and therefore the pH is going to be higher in value. But slightly, because again, this is a very weak base. Or if we have more acid on the bottom and less of this A minus, then this logarithm is going to be lower. Then the pH is going to be lower because the buffer is going to be more acidic. But then again, slightly lower because the HA is not such a strong acid, it's a very weak acid. I would like to also mention that some people might write this Henderson-Hasselbalch equation as in this form. These are essentially the same. All they did was take this negative log Ka, and we know that negative log stands for P, because the P in pH stands for negative log, so this negative log is the same as P. So they just took that and summarized it with this P and left this Ka. So it's plus pKa, but it's actually plus negative log of Ka. So it's the same thing, just it might cause a little bit of confusion if a person does not know what this P stands for. Now let's apply the Henderson-Hasselbalch equation to solving for the pH of a buffer. Let's say that we have a buffer with 1.5 molar of NH4 plus and 1 molar of NH3. Both are dissolved in water in the same solution. The Ka, this is a given, of NH4 plus is 5.56 times 10 to the negative 10th. And we need to find the pH of this buffer. So let's just see what's going on here. We know that the NH4 plus is the weak conjugate acid because NH4 plus gives an H to H2O to make some NH3, which is its weak conjugate base, and H3O plus. And this NH3 can take some H's from H2O and make some NH4 plus backwards. So there's a weak conjugate acid and there's a weak conjugate base. And we know that in the Henderson-Hasselbalch, and they're also, forgot to mention, their initial concentrations once they're added don't really change because again, they are so large, 1 molar and 1.5 molar, let's say relative to this tiny Ka, 5.56 times 10 to the negative 10th, that this reaction is so weak that it doesn't really change their initial concentrations. We can ignore these changes to their initial concentrations. We also know that the Henderson-Hasselbalch equation states logarithm of the weak conjugate base concentration over the weak conjugate acid concentration minus the logarithm of the Ka constant for this HA equals the pH. Well, then we just plug in the logarithm of the weak conjugate base, in this case it's NH3 because it's here, over the weak conjugate acid, NH4 plus, minus the logarithm of the Ka, which is given above, equals the pH. And then it's very simple. Logarithm of the 1, which is the concentration of NH3, over the 1.5, which is the concentration of NH4 plus, remember it's molar, minus the logarithm of this Ka, which is 5.56 times 10 to the negative 10th. And we get a pH of 9.08. So it's a very simple problem actually, because all we had to do is just plug these three things in and we get the answer automatically right in one equation without having to do this multi-step process like we did for the other buffer pHs. Part 14. Buffer pH after addition of strong acid or strong base. So let's say that we have a buffer, and I'm going to use the same buffer as I used before. We have an equal concentration of NH4 plus, the weak conjugate acid, and the equal concentration of NH3, the weak conjugate base. Let's say they're in a 1:1 molar ratio. And then we add this super strong acid, because we know it's one of our strong acids from our list, HCl. And what happens when we add this HCl, 0.5 molar of it to be precise, is that it completely dissociates, completely. There's none of this original binded HCl remaining. Instead, we get 0.5 molar H plus ions, and 0.5 molar of the Cl minus ions, but since they're neutral, we don't care about them. We only care about the H+. So this 0.5 molar H+ goes into this buffer, and all of them, if there's a lower concentration of them than NH3, then all of them bind to the NH3, and by binding to NH3, the H pluses help to create more of this NH4+ backwards. So I'm drawing here minus 0.5 molar because all of these H pluses bind to NH3. Now they're not alone in the solution now anymore. And this NH3, originally we had 1 molar of it, but since 0.5 molar of it binded to H plus to make NH4+, now there's 0.5 molar less of it. And since 0.5 molar of this and this binded together to make NH4+, then we have 0.5 molar of NH4+ forming. So now our concentrations in the buffer are not 1 to 1, they're instead 1.5 to 0.5 because NH4+ concentration increased to 1.5 molar and the NH3 concentration decreased to 0.5 molar. And that's all that happened after we added its HCl. Now, here's where people get a little bit confused as to how the pH of this buffer changes. They think that once we add this 0.5 molar HCl and these concentrations drastically change, then something has to happen. Something has to happen to this or that concentration, they have to continue changing. But that's not the reality. What actually happens is that originally we had this 1-to-1 molar ratio, and these concentrations, because they're so large, and these reactions between them naturally are so weak, because one is a weak acid, one is a weak base, these initial concentrations essentially do not change. So once we add this HCl and it causes this drastic change in concentrations, people assume that, oh, now that there's a drastic change, something has to happen to their concentrations after they change. But the truth is that nothing happens. Once these new concentrations are formed, once we have 1.5 molar instead of 1 molar, and 0.5 molar instead of 1 molar, these new concentrations also remain static, they remain the same. Because again, after this HCl reacted completely, these things establish an equilibrium again. And to establish this equilibrium, not much of this and not much of this actually reacts, because these are so weak. So again, the concentrations of these are still too large to really change. So they don't change. So once we have these new concentrations established, they also don't change like these original concentrations. And then we can just plug these new concentrations into our Henderson Hasselbalch formula, equation, I mean. And then we can get the new pH for the solution. And I guarantee that it didn't really change from this pH, because it didn't change that much, I mean. It's slightly more acidic because we have some more NH4+ forming, but didn't really change by much because NH4+ is such a weak acid and NH3 is such a weak base that they don't really change the pH when their concentrations change drastically. So again, just to recap, after we added the strong acid, it caused a regular stoichiometric change in their concentrations. We don't even need to know the Ka for the strong acid, we just need to know that it's strong, that completely dissociates and gives 0.5 molar to NH3 to form an additional 0.5 molar of NH4+. And these new concentrations are established. And then you can say that these concentrations remain static as long as we don't add any more new strong acids or strong bases. And then we can calculate the pH based on these new static concentrations. Now I would like to continue the same example, but in this case I'll add a very strong base. So again, we have our buffer of NH4+, 1 molar to 1 molar of NH3. Then we add this 0.5 molar of this strong base. We know it's a strong base from our chart, sodium hydroxide, NaOH. And this sodium hydroxide, because it's a strong base, completely dissociates to form 0.5 molar of OH- and 0.5 molar of Na+, but this Na+ we don't care about because it's a neutral ion. So 0.5 molar is the only thing that actually affects the pH. And when this 0.5 molar enters the solution, it reacts with NH4+, because it takes as many H pluses from this NH4+ that are available to take. So if there's, let's say, 0.5 molar of these NH4+ that can be taken, then this will take it. So in this case, since we only have 0.5 molar of OH-, it's going to take exactly 0.5 molar of these H pluses to form an additional 0.5 molar of NH3. and the water concentration we don't care about. So in this case, the NH4 plus concentration decreases by 0.5 molar. The OH minus concentration also eventually decreases by 0.5 molar, since all of it gets converted to water, essentially. And the NH3 concentration increases by 0.5 molar, because this NH4 plus got stripped of 0.5 molar H pluses to form an additional 0.5 molar NH3. And now our final concentrations would be 1 minus 0.5 is 0.5 molar of NH4 plus to 1.5 molar of NH3, 1 plus 0.5. And originally we had 1 molar to 1 molar, now we have 0.5 molar to 1.5 molar. So again, this initial concentration before we added NaOH was static. It was essentially unchanging because these reactions in between them are pretty weak. They're both weak substances. And then after we added this NaOH, their concentrations drastically changed because these OH minuses are very strong. And now we have these new concentrations established. And these new concentrations also remain constant, essentially constant, because again, the reactions between these two are pretty weak. So now we can just use these new initial concentrations, no, not initial, I mean the new concentrations to calculate the pH using our Henderson-Hasselbalch formula, and I'll show you an example right now. Alright, so this is going to be an example to show how we find buffer pH after, let's say, we add a strong acid or strong base. In this case, I'm going to show how we find the buffer pH after we add a strong base. So let's say we have a buffer with a 1 molar concentration of NH4+, our weak conjugate acid, and 1 molar concentration of NH3, our weak conjugate base. The Ka for NH4+ is equal to 5.56 times 10 to the negative 10th. We need to calculate the pH change of the buffer after 0.5 molar of NaOH, a strong base, is added. So, in order to calculate the pH change, we need to know the final pH and the initial pH. So the final pH minus the initial pH is our pH difference. So let's start out what actually happens in this buffer reaction. Well, these NH4+, the NH4+ and the NH3 are present in a 1-to-1 ratio, and they have these weak reactions going on between them. For example, the NH4+ sometimes gives H's to the H2O to form some NH3 and an H3O+, and the NH3 can take some H's from H2O to form some NH4+ backwards. But remember, these reactions don't really make a difference in their initial concentrations. Now we know that the Henderson-Hasselbalch equation for this buffer reaction would be a logarithm of NH3, our weak conjugate base concentration, over our weak conjugate acid concentration, NH4+, minus the logarithm of the Ka equals the pH. We can use this to find the initial pH, because we know that we have 1 molar of NH3, our weak conjugate base, and 1 molar of NH4+, our weak conjugate acid, so 1 over 1, minus the logarithm of our Ka value, which is in this case 5.56 times 10 to the negative 10th, and we get this initial pH of 9.25. Sweet. Now let's see how these concentrations of NH4+ and NH3 change so that we can find the pH of the buffer after our NaOH was added. So when 0.5 molar of NaOH is added, it completely dissociates. Almost none of that binded NaOH originally remains. Instead, we get 0.5 molar OH minus and 0.5 molar Na plus into the solution. Na plus is a neutral ion, so we don't care about it. We only care about this 0.5 molar of OH minus. The 0.5 molar of OH minus then reacts with the weak conjugate acid, because the base reacts with the weak conjugate acid, or if this was, let's say, acidic, it could react with the weak conjugate base, but in this case, since it's basic, it reacts with the acid. And all of this OH minus takes in H's from the NH4+, because it's such a strong base. We don't really care about Ka's or Kb's. This is just stoichiometry. If 0.5 molar of OH minus is added, then let's say it's going to take 0.5 molar of H+, no matter what. So our concentration of NH4+ decreases from 1 molar to 0.5 molar, because 1 minus 0.5 is 0.5, since 0.5 molar of this NH4+ react with 0.5 molar of OH minus to form an additional 0.5 molar of NH3. So our concentration of NH3 increases from 1 molar to 1.5 molar because added 0.5 molar. So now in the end, after the NaOH was added, we get the concentrations to be NH4+, is now 0.5 molar, and NH3 now is 1.5 molar. And remember, these concentrations, after the strong base was added, these concentrations remain stable. Because once the strong base was added, they stabilize immediately. Because again, these are weak acid and base, these are weak acid and base, and the reactions between them are so little that their concentrations essentially remain constant after this NaOH was added. Now we can use the Henderson-Hasselbalch equation again to calculate the new pH of this solution. So now we know that the weak conjugate base has a concentration of 1.5, we draw it on the top, and the weak conjugate acid has a concentration of 0.5, we draw it on the bottom. So logarithm of that, minus the logarithm of the Ka. The Ka never changed, it's always constant for this NH4+. So 5.56 times 10 to the negative 10th. And that will equal the new pH of the solution after the strong base was added and reacted with this NH4+ and NH3, and their concentrations now are new concentrations, but they remain constant. And so for this ratio of concentrations, we get the pH of the solution to be 9.73. That's the final pH of the solution after the NaOH was added. So now we subtract our final pH, our initial pH from our final pH. So our final 9.73 minus the initial 9.25, and our pH difference is 0.48, and that is how you can calculate the pH of after we added a strong acid or strong base, and then get the difference in pH.